that. So for electron, we need a quantized electric charge. Yes, and we can get electric charge quantization by the topological. So like Hedgehog is a simplest topological charge and it is quantized. So here we get quantized electric charge. For electron, we also need angular momentum. Yes, that there is something rotating, not perfect point, but the field itself. And indeed, we get the rotation of the field itself. It also it corresponds to the clock, the Zitterbewegung, and also it's needed for magnetic dipole moment of electron. And for neutrino, I would like to convince you to this kind of picture. So we need topological vortices from many perspectives. I try to show. And for example, in QCD, there are these quark strings, gluon flux tubes modeled as topological vortices, and they should also form these closed loops. And so they should correspond to some particles. And looking at properties, they seem in perfect agreement with neutrino. So, for example, there are very light and stable in three families. Then they can oscillate between these families, and they can be created in beta decay. I will mention. Okay, so let me go to the slides. So the big question is why they want to rotate. Yes, what propels this clock, this Zitterbewegung? So I would like to convince you to this curvature coupling mechanism. That in many models, for example, in Skyrmion model, we need this kind of term minus curvature square. So there is minus and there is curvature square. It is Lorentz invariant. And what's inside? So this is in energy. So if the phi1, the spatial derivative of one field, the shape of particle is non-zero, then it gives energetic tendency for psi zero, temporal derivative of quantum phase, yes, or something more general. Yes, so it literally, this kind of term gives preference for some rotation of the field due to presence of particle. Yeah, so this is exactly what we need, and it appears in many models like Skyrmion model and what I will show. So first of all, why curvature? So we need curvature for the quantization of electric charge, for example. So electric charge we calculate with the Gauss law, that integrating electric field over the closed surface, we get the electric charge inside. But this basic Gauss law can return a real charge, a real number. While in nature it should be integral multiplicity of elementary charge plus quarks, I will also talk about. So we can use this topological version, the Gauss-Bonnet theorem, that we have some deeper field n, let's say of unitary vectors, and we define the curvature as our electric field. This way, the Gauss law counts the topological charge. So literally, the wrapping number, how much time that the sphere wraps on the sphere. So here is the Lagrangian I'm considering. So F as in electromagnetism. However, this F is curvature of some deeper field, like here. It's dual curvature. So using standard curvature, you get magnetic monopoles. Using dual, we get electric monopoles as quantized charges. Yes. So the field I'm using is like in liquid crystals. It's called the Landau-de Gennes model. That we have some tensor real symmetric field, which eigenvalues define the shape of our molecules. Yeah, so here is, let's say, one is the long axis, and we also recognize the second axis and third in 3D. Yeah, so we get kind of molecule with three different axes. Finally, also the temporal axis for gravity. Okay, so let me start with the Sine-Gordon model. So there is this one-dimensional, very simple model which can be realized by just lattice of pendula, like here. So this pendulum want to be down, yes, due to gravity, but there is down here, and also 2 pi farther, there is also down. Yeah, so we get many vacuum of minimal energy. So this configuration from going from one vacuum to another is stable, has some minimal energy, and it has imprisoned some energy. Yeah, so literally as mass of the particle. So due to this mass, it is slowed down, and now we get literally the Lorentz contraction. Here is resting, here is moving. We can see it's contracted exactly as in special relativity. Yeah, so this very simple model creates charge quantization, massless massive particles, Lorentz contraction, also time dilation. So having this lattice of pendula, if you take one and let it rest, we get these oscillating solutions. For example, breeders. So here is the position, here is time. We get these oscillations. But now here is a resting breeder. But now if this breeder travels, we get a relativistic time dilation. Yeah, so we get also exactly like in special relativity. However, these breeders can be calmed down to zero. So we can take this energy and then we slow down to zero. So the big question is how to make it the time crystal, how to make it periodic already in the lowest energy scale, lowest energy. So here is this toy model, how to make the king um, also time crystal. So here is our king. And now, so here is the Hamiltonian of standard of the phi-to-4 model king. And now we add this curvature coupling. Yeah, so again, so here is this phi1 is the spatial derivative. So in the presence of particle, it's non-zero. Yeah, so this shape of particle makes it non-zero, and it gives tendency for a non-zero temporal derivative of our quantum phase. Yeah, so literally this term makes us that the frequency of this omega should be non-zero. So here we can look at energy of depending on this omega. And we can see it's not minimal for zero, but for some non-zero frequency. Yeah, so we get literally time crystal king. In due to energy minimization in one to rotate, like here. So here is this is time model, and here is the complete model it came from. So here is the Lagrangian I am using, yeah. So F mini F mini. So for standard electromagnetic Lagrangian, just two indexes, F mini, F mini, going from Lagrangian to Hamiltonian to energy density, we get only positive terms. However, so here we use four indexes because this is curvature for us. And full curvature are four indexes. Going with four curvatures from Lagrangian to Hamiltonian, we get both positive terms, those and negative terms. Yeah, so I'm sorry, I'm sick today. So we need this. So we literally get this negative curvature terms we need for the propulsion of the clock. So here is this F mini written for our case. So here are the positive terms. They correspond to electromagnetism, quantum mechanics, and gravity. I mentioned further. And here is the clock propulsion, which is negative term. Yeah. So in Hamiltonian you get this kind of term, which says again. So here is this time derivative. It literally is twisting of this long axis of our field. And here are boosts for gravity. This term gives a tendency for both gravitational mass of the particle with this boost and clock temporal derivative, this twist of the field with time. So this is exactly what we need. Okay, so let me go further. Let me start from the lower level. So there is this analogy between electromagnetism and hydrodynamics. Yeah. So especially with the B field, the magnetic field corresponds to the omega, also in the Barnett effect, so which is an electromagnetic effect. So here is this basic analogy, and the A field corresponds to some velocity of some fluid. Yes. Also in Barnett effect, it's very similar. So also there is Lorentz force, and the analog is the Coriolis force, and it is applied, for example, in this very nice Zeeman effect by this Kuder, one of the Kuder articles. So in this link, so they get these pairs which are rotating fixed frequency, and now we start rotating the entire fluid tank, and the Coriolis effect increases or decreases the distance between them, acting exactly as in Zeeman effect. Okay, so we can get electromagnetism with dynamics of superfluid. However, there are missing the point-like particles, the charges like electron. So how to add the point-like defects? We can do it in liquid crystals that they do it. They get Coulomb-like interaction for quantized topological charges. Yeah, so there are many articles. If for example this kind of plot that we get two topological charges and look at the evolution with time, and they can fit some long range interaction. What strength they get. Yeah, so we can extend this electromagnetism for the superfluid with point-like particles like electron by going to liquid crystals. And so here is this topological Gauss law. Yeah, so standard Gauss law integrates electric charge to get electric field to get charge inside, and we get this topological version which uses curvature here. Yes, and this way we get literally. So we have field of unitary vectors, let's say on the sphere, and we count how many times this sphere wraps around itself. So it has to be integer multiplicity of 4 pi. So finally, so here is this basic approach that we have some deeper field and field, for example, unitary vectors. We define its affine connection, local rotation, and then the curvature, and use standard electromagnetic Lagrangian using this curvature as the F tensor. Yes, and this way we get electromagnetism with built-in charge quantization as topological. So here is, for example, the creation of pair. So positive charge, negative charge from nothing, but from energy. And we can also, looking at this picture, you can also understand what are the virtual pair creation. Yeah, so to create electron plus positron, we need to go to this entire process. We need 2 times mass of electron energy, but we could go only here and go back. So we could get kind of perturbation of the field toward pair creation, which needs lower energy is sufficient for that. Yeah, so and from Feynman diagrams, it will be virtual pair creation, just going here and go back, let's say. Okay, so here is this Coulomb interaction as effective behavior potential for the two topological charges. So here is energy density by colors for two positive charges, topological. Here is for positive and negative. So here we should get repulsion, here we get attraction. And so here is calculation of this effective potential. So we place them in this distance and calculate, integrate the Hamiltonian, the energy density, and get the dots. Yes, and the dots, when fitting to 1 over Coulomb-like potential, we see that is perfect. Yes, so it's perfect Coulomb-like potential. So there are some approximation. We doing it right. We also get we also need his cutoff. So here we cut the singularities. Doing it right, we should regularize it with Higgs potential, what would lead to running coupling effect. But I'm skipping it here. We can discuss further. Okay, so very similar Lagrangian as I'm using is using these Kermian models where they get these models of nuclei. So with this is one of kinetic terms of Lagrangian they use. And again, these are curvature squared as I'm using. So this is very similar to Kermian models, but the difference is that we are using the Higgs-like potential. So the minimum of energy is, for example, unitary vectors. This leads to a long-range interaction like electromagnetism, quantum mechanics, gravity, but they use trivial potential, trivial minimum. So if nothing happens, the field has to go to this minimum. So they get only short-range interaction like Yukawa. So they model nuclei. And they say that this topological charge, we have just one such value, and they say it's baryon number. They don't have electric charge. So in their view, the baryon number cannot be changed. It's ideally conserved. However, in physics, there are these two processes which require violation of baryon number, baryogenesis and Hawking radiation. So that's a big question. Is the topological charge baryon number or maybe right electric charge? And I think the electric charge is much more appropriate. Okay, so let's go further. So here is the evolution of our field. So we have this field of elongated molecules, kind of, and they can tilt. These are the green parts, and they can twist, which is a lower energy. So literally, there are high energy contributions and low energy contributions from rotations, and these two recreate electromagnetism, the F mini part of QED Lagrangian. But there is also this low energy term with H bar C of contribution of quantum phase. Yeah, so we also need this term, and it can be obtained by this recognizing these twists as low energy contributions. And finally, there are also the boosts, the gamma. So SO3 requires also for Lorentz invariance requires also to allow for boosts. And turns out that the boosts lead to second set of Maxwell equations, which are called the gravity electromagnetism. Yeah, so this way by SO3, SO13, vacuum dynamics, we get all three. Electromagnetism, the green one, plus quantum mechanics, the blue one with Klein-Gordon-like equation, plus the second set of Maxwell equations for the boosts. So there is very nice unification by just the dynamics of SO13 Lorentz group. Okay, so there is also interaction between these two fields, the gravitational and these spatial rotations. For example, this slowing down of electromagnetic propagation in gravitational field. So this is called as its varying speed of light, and it gives both the gravitational time dilation that every chemistry is based on electromagnetic propagation. So if you slow down it, we get the time dilation, and also the light bending to the Fermat principle. Yeah, so that the light chooses the shortest path. We can also get gluons from by this deformation, but let me skip it. So here is this another view. So we get this hedgehog and also recognize this twist of our field. So we get contributions of various energy size. So here is this electromagnetic contribution, and here is the quantum contribution into this QED Lagrangian, as mentioned. So finally, we can see that there is electromagnetic field. We assume there is deeper A field because, for example, of Aharonov bomb effect. And here we say that there is even deeper field, like this field of unitary vectors on SO3, these molecules, like here, such that A field is connection derivative, and F tensor E bit are its curvature. Yeah, so there is even deeper field to make Gauss law count topological charge. So to build in charge quantization as topological, we need even deeper field. So for example, this momentum operator has one derivative, but this A is also here a derivative of some deeper field. Yeah, so again, A field is always seen as some velocity, some derivative of deeper field, and here indeed it is they are unified. Like here, there are this Aharonov bomb effect for hydrodynamics, again using this analogy. Okay, so let's think about further topological defects of liquid crystals, for example. So in 3D, we could get the domain walls. However, for liquid crystals, if you have this kind of molecules which don't recognize this and this, then there are no domain walls. So we don't have the domain walls for liquid crystals. We need these two types. So vortices, topological vortices, and point-like charges. So point-like we interpret as quantized electric charges in dual formulation. And the vortices, there are many arguments that are also there in physics. I will show you in a moment. But for example, for quarks, we need both. So for quarks, there is belief there is this quark string between them to make the force asymptotically linear, asymptotic freedom and confinement. So here we have this topological vortex for quark strings, and now we need the electric charge for quark. So here is rotating it inward outward by pi, you'd get elementary charge. But you could also perform only pi third. And now it is literally 1/3 elementary topological charge as electric charge. So we get literally quark, anti-quark. Yeah. And there is a conflict between them, which with asymptotically linear energy per length. So as required for QCD. So what about the Gauss law? So the Gauss law, to get the fractional charge, would have to cut this topological vortex, and here is a singularity inside. So it can lead to non-integer charges. So finally, there is this string hadronization. So they are using for LHC collisions this assumption that there is created this quark string and it decays into particles. So if we ask what is this quark string, the only concrete non-perturbative pictures I have seen are topological vortices. So we need to just find the correspondence what this topological vortex can decay into and what they observe in LHC collisions. Yeah, so we don't need just this correspondence, and searching for it, everything seems to agree. Okay, going back to electron, so electron has both the electric charge quantized and the magnetic dipole moment and angular momentum and the clock. This kind of configuration seems to agree with all these properties. Evolving configuration, yeah. So we have angular momentum also and clock and magnetic dipole moment. And so now we need this now we can get these three types of electric charge as topological. So Hedgehog of one of the three axes, if you distinguish them. So topologically they are the same charges but with different regularization. So the same charge, different mass, like the three leptons. So I think this is promising for the three leptons. So now let's go to neutrinos. So people think about them as perfect points. However, this is only perturbative approximation, like this apple plus apple equals to apple. So it is true, but still we can ask about the deeper structure of this apple, like also for neutrino. We have some point as a perfect point in the Feynman diagram, but we can still ask what is the field configuration inside. And recently there was this news that neutrino has turned out 1,000 times larger than nucleus. Yes, so it looks like this, that the beryllium captured electron and went to lithium 7 and produced neutrino. And then they looked at the recoil of this nucleus, lithium 7, and got this plot, and they focus on this energy histogram. And from Heisenberg principle got that delta x of size like 6 picometers. So 1,000 times larger than nucleus. So the big question is, what's happening in this huge size? Yes, 6 picometers. Some field configuration. What is it? So there are some arguments that we need these topological defects in real physics. Yeah. So there are not only point particles but also real vortices, one-dimensional structure which are very stable. So the nicest argument are these sun's corona, that they see these shining lines in sun's corona, and they don't understand what's happening there, but suspect that this is topological stabilization. Why they not dissipate but remain stable shining lines. And another argument is for halonuclei, that we have this nuclei like lithium 9, which has two nuclei in distance much larger than on strong force. And there are many others arguments also. They are just needed. If you have the quantum phase, if you have a loop where the quantum phase makes like 2 pi, then through this loop there is a singularity, the topological vortex of this quantum phase. Yes, so there are many arguments that there are some one-dimensional structure, topological structure in microscopic physics also. These topological vortices are required for superconducting in superfluid. So, but the question is, are they also required for vacuum? And these quark strings, these quark-anti-quark pairs, seems a very nice. They require this kind of structure. So the string theory was started with this quark-anti-quark having linear energy when you take them apart. So for short distance for quark anti-quark is Coulomb-like, and then it goes to linear. So the question is how to get the linear dependence, and this way we get the linear dependence. Yes, so by defining some string which has energy density per length, and here we get this 1/3 charge, topological charge as electric minus, and there is some asymptotically constant. Shape some conflict inside. So asymptotically, you would have to have this 1 GeV per femtometer for QCD. So it agrees with the QCD. Okay, so now there is this halonuclei, yeah, so like lithium 11. So we have the core, but then like 5 femtometer further, there are two neutrons, and for milliseconds, so these very long times, where the minimum of energy for nuclear force is like below 1 femtometer. So what binds them is that's a very difficult question. And even more, there are also protons, 1 or 2 protons can be here. So we have Coulomb repulsion, and still they are here for milliseconds. So again, we need some very concrete mechanisms to bind them. Yeah. So we can assume some effective models. We just put in by hand, but what binds them? Yeah. So I think the topological vortex could be the only answer. That there is literally some topological vortex going from here and here. Okay, so now let's go to the string hadronization, that in LHC collisions they assume there is created such quark string like here, and it decays into particles. So we need to find the correspondence. Yeah, so from one side, this topological vortex can decay into the simple loop. So as mentioned, there are three types: very light and stable, and they seem to argument with neutrinos. I will continue further. Then they can form simple knots. So here is one vortex in the center and the second around. So what's happening? The vortex around deforms the configuration inside toward the hedgehog, and the hedgehog for us is a charge. So now it can enclose this hedgehog, forming a proton. Yes, so he is positive charge, and for neutron there is positive charge from the baryon structure, and now this has to be compensated. So we get this kind of quark structure. So plus from the structure of baryon itself, and then it has to be compensated, leading to higher energy, explaining why neutron is heavier than proton. And finally, we could get this strangeness decay. The number of twists of this vortex seem to agree with strangeness. So here would be so we have a strange baryon with vortex inside, and it releases part of the strangeness. So it agrees well with this strangeness decay. So by one reduces strangeness by 1 through 2 pion, or by 2 by count. Okay, so here are more arguments for this picture. So so there are some articles claiming that neutron has indeed positive core, negative shell. There's 3 articles. Then for the deuteron, both baryons require some charge from structure, and now they can share this charge. So we have plus here, and minus. Yeah, so we get plus, minus, plus. So we get electric quadrupole moment. Yes, and we know experimentally that deuteron has electric quadrupole moment. So this is natural explanation why. Yes, naively, proton plus neutron should not have electric quadrupole moment, but so we need some charge deformation, what is generally called this EMC effect, that the quark configuration of nuclei is completely different than of single nucleons. Okay, so now let's think about the quarks, the 6 quarks. So we get these 3 times of the topological vortices, and now we get this 1/3, minus 1/3. So they would be required for this neutron to compensate the charge, and then there can be this vortex around. And for vortex around, as here, there is required some charge. So it is energetically preferred to be plus 2/3 because of the structure. Yeah, so we can explain why plus is why U is lighter, because it agrees with this vortex around. And for neutrinos, assuming this kind of simpler loops, we can understand why we have these two mixing matrices. That for quarks is very difficult to rotate, but for neutrinos it's easy to rotate, because it is much easier to rotate this kind of field than the knot. Yes, it's not it blocks this kind of rotation. So it is much more diagonal mixing matrix in contrast to the neutrino. And here's for neutrino, what the final slide nearly. So, here we have 3 neutrinos from beta decay. So here we have this beta decay. So neutron shifts charge and releases energy as this loop as required, very light and stable. So oscillating, we can explain energy conservation. Because there will be energy per length. So going to different flavor, the length of the loop can change. We can also explain why there's left-handed neutrino, right-handed antineutrino, because they have the same gravitational mass, the tilde part, but opposite the spatial derivatives and temporal. And this is the summary. Yeah, so you have this huge standard model Lagrangian, which kind of epicycle. Something didn't work, so they added more terms. But it should be some Taylor expansions of some very simple model. Yeah, so which is effectively described by this kind of huge Lagrangian. So where to search for this simpler model? So it should have electromagnetism. So some F mini is required, right, to get electromagnetism at the start. Yeah. So and also liquid crystals are electromagnetism not enough. It's also topology to get point charges. And liquid crystals, if you do it this way, very simple model, get everything. Electromagnetism, quantum mechanics, with Klein-Gordon-like equation, Gauss second set of Maxwell equations, leptons, neutrinos, baryons, proton, electron, and Newton. So everything's qualitatively seems to agree, but it needs a lot of quantitative work to finally show that effectively is described as something similar. Yes. So thank you very much for the attention. And the next person can switch and present. Perfectly. Yeah, so once again, so here is the topological charge, here is the angular momentum, a magnetic dipole moment, and clock. here we have the oscillation between muon and tau neutrino. So electron would be is completely different. An electron would have would be along the first axis or the second axis or the third axis. So electron is completely different, and they know electron is completely different. Yeah. So there is mostly oscillation between muon and tau. It should look like this. That's rotation between second or third axis along the loop. Who is the next?
I think I am next.
Okay, sure. So you can share your screen.
Let me try.
Sorry, Jarek, just a question. There is no time for a question in between the talk, or is it at the end of the seminar, the
yes,
question?
unfortunately, so yeah, so maybe some brief the question. Sure. And unfortunately, yeah, as usual, the schedule is extremely packed. Yeah, I'm sorry. So sure. So if you have some short question, or we can discuss on chat generally.
Yeah, later. Don't worry. I will let Andras talk. Thank you.
Sure. Thanks. Okay, please start.
Okay, I will start my presentation. Yeah, try to go to presentation mode. Do you see my full screen now?
Yes.
Okay, and it's switching slides. Okay, great. So hello, my name is Adras Kovacs, and I will be talking about transversal and longitudinal electromagnetic waves. Yeah, this presentation is an interesting complement to Jarek's presentation, because many of the themes that Jarek brought up will be also present in my presentation, but from a different perspective. Now, these ideas or results that I will present are motivated by my co-authors, and it is the result of a quite long thought process. And my work recently has been supported kindly by Marc Fleury, who's also on this call. Now, specifically, what I will be focusing on is to understand which type of electromagnetic wave is present in Zitterbewegung, and how to even understand longitudinal electromagnetic waves, because that's not something we find in standard textbooks. And also I will address hydrodynamic analogy. But so what I will start with is the context. The context is the evolution of fundamental forces perception. And there are two themes shown on the left and the right, which will be converging. So on the left, the main event that is very important from our point of view is Einstein's insight that we can think of gravity not as a force, but as a manifestation of space-time curvature. So that means that when Earth is going around the sun, Earth really thinks it's flying in a straight line in local space-time, but globally the space-time is curved, so the local straight motion is actually a curved motion when looking from far away. And this naturally leads to the question, can electromagnetic interactions also be written in terms of space-time curvature? Einstein thought long about this question, but he did not get any useful results. Then shortly after him, Hermann Weyl also formulated an attempted formulation of writing electromagnetism in terms of space-time curvature, but this was also not successful. And there were a number of others. I would like to highlight here a most recent attempt, which in my opinion is the best attempt. It's by Finnish scientist Jussi Lindgren, and Jussi has succeeded, in my opinion, to write Maxwell equation in terms of space-time curvature, and he shows that electric and magnetic forces can also be thought as manifestations of space-time curvature. And in course of doing so, he realized that the only way this can be achieved is to formulate electric charges also as a manifestation of space-time curvature. You cannot just look at forces and charges separately, but you actually have to address the difficult question of how to formulate electric charges as well in this geometric framework. So the result is this article, Electromagnetism as Purely Geometric Theory, and it will be soon published in Journal of Physics. So the other thread on the right concerns Maxwell equation itself. So Maxwell equation is a differential equation of the vector potential field plus electric charges. In essence, electric charges are put into it by hand, so it doesn't answer the question of what the charges themselves made of. And if one wants to formulate a theory, a field theory, then a natural question is to ask, can we formulate Maxwell equation purely in terms of electromagnetic fields? Can it be written as a pure field theory? And there has been a few attempts at that at the middle of 20th century. And here I'm highlighting the most recent attempt, which again, in my opinion, is the most successful attempt accomplished by Giorgio Vassallo. So he writes Maxwell equation as a purely field equation. This is also the simplest formulation of Maxwell equation, and it's a gaugeless electromagnetic field equation. So his results are published in this article, Maxwell's equation and Occam's razor, that was published already in 2017. Now, I did look at both of these articles and look the correspondence. And what is interesting is that they really show the same physics and the same picture. So it's two different type of approaches, but they converge to the same point, and they are just two aspects of the same model. And I thought that's very interesting that two very different approaches and thoughts finally lead to the same physics. So, so I encourage everyone to read these two articles. And in the following part of my talk, I will take these two references as the starting point, and I will be calculating starting from these. Now, here comes the question of hydrodynamics analogy, which was mentioned by Jarek before. And in this slide, I'm showing a table that's compiled by Olivier Rousselle, who's also on this call today, that shows how we can look at the analogy between various quantities and measures from fluid dynamics and from electromagnetism. And what you can see is that in fluid dynamics, we are concerned with calculating and modeling fluid velocity. And if we want to have the equivalent picture on electrodynamics, then we have to consider the vector potential A as some kind of motion or speed that is equivalent to the fluid velocity. So the analogy starts from this equivalence, and then you can see that for almost every hydrodynamic quantity, we can find a very analogous electromagnetic quantity. Now, this is very nice so far, but when we think of the waves, then this leads to a problem, because in fluid dynamics, we have longitudinal waves, but in electromagnetism, we see only transversal waves, right? That's what we find in the textbooks when we look at what light waves or what radio waves we have. And then that's surprising, because given all these analogies, why would the waves be so completely different? Also, if you look at the Coulomb gauge condition that is often used in electrodynamic calculations. You can find that it corresponds to the fluid incompressibility condition, and by applying a fluid incompressibility condition, you are eliminating any possibility of longitudinal wave, because longitudinal wave presupposes a compressibility. So this somehow indicates that by applying gauges to electromagnetic theory, we are cutting out part of the solution, and so maybe we are losing one part of the theory which describes longitudinal waves. So we have to look at the formulation of electromagnetic theory that encompasses the full picture and allows both longitudinal and transversal waves. So this kind of formulation is given by the gaugeless electromagnetic theory of Giorgio Vassallo that is described in reference 2 that I mentioned. And to get the dynamics of waves, we have to start from the Lagrangian formulation, and the Lagrangian will give then all the dynamics of the field evolution. And here on the left, you can see Giorgio's formulation for the Lagrangian of the electromagnetic field. And I contrast it to the standard model Lagrangian of the electroweak theory. And so this thing on the right is a monstrosity. And the only reason I show it is just to convey that when you hear people talking about standard model electroweak theory, it's really this type of monster Lagrangian that they have in mind to work with. Okay, but our focus will be to understand the Lagrangian on the left. So what you see is that it's a very simple expression of the electromagnetic vector potential. So you take the vector potential and you apply the space-time derivative. That's this sigma operator. Now, this application of the space-time derivative is done under space-time algebra. So that's the geometric algebra of our space-time. And this multiplication is the corresponding Clifford multiplication. But essentially, this gives you the electromagnetic fields in this geometric algebra. And the Lagrangian expression itself is just the norm square of the fields, right? So it's a very simple conceptually that your electromagnetic Lagrangian is nothing else but the squared amplitude of the electromagnetic fields. And you know, sometimes I ask the question why I write this with Clifford algebra, why I don't use normal Euclidean operators. Well, it's possible to make it more complicated, but you know, I do not want to make it more complicated because space-time has a geometric structure that's different from the Euclidean geometry. And in order to see that geometry clearly, we should use, in my opinion, the corresponding geometric algebra. Otherwise, we have a risk of getting lost in the notation, whereas here the notation is very clear. All right, so this is the Lagrangian we're going to be studying. And I think everybody in the audience is familiar with Lagrangian mechanics. In any case, I have two references here at the bottom of the screen that may be useful, that are probably useful to highlight the importance of Lagrangian approach when studying electromagnetic waves and quantum mechanical waves. I personally learned Lagrangian mechanics in the context of mechanics bodies, and it was in my education not as much emphasized how crucial it is to understand the motion and properties of waves. So that's why I saw that these videos that I have here, they are very nice introduction to show you why the Lagrangian approach is a very useful and powerful formalism to understand the dynamics of the electromagnetic waves. All right, so now let's go ahead and unpack this Lagrangian in terms of electromagnetic fields. So this algebra that you see here is just unpacking this space-time derivative of the vector potential in terms of the electric field, magnetic field, and scalar field. So, so normally we see only electric and magnetic fields when we work with electromagnetism, and in the traditional approach to electromagnetism, the role of the applied gauges is to eliminate scalar fields. But here we work with a gaugeless theory, and we want to look at all the components of the fields. We do not want to eliminate anything. And the interesting thing when you look at this Lagrangian in terms of written in terms of fields is that it has two components circled by this red and blue ellipses. The red ellipse is the Lagrangian of the transversal electromagnetic fields. So this part in the left, it's 0 for a uniform transversal wave. So what that means is that the electric and magnetic fields induce each other in such a way that this overall expression remains 0. And when you look at the right side, it is really clear, it is shouting at you that this is a longitudinal wave expression. The electric and magnetic fields are parallel. And so this right side, that is a new result from Giorgio Vassallo's approach, is the longitudinal waves Lagrangian component, right? So as before, this longitudinal Lagrangian is also 0 for a uniform electromagnetic wave. So what it means is that the electromagnetic scalar field and the electric and magnetic field, they induce each other in such a way that the overall Lagrangian remains 0. And both of these components are Lorentz invariant as expected. So now this is a very nice result that we got a Lagrangian expression that is decomposing into longitudinal and transversal parts. And let's look into the longitudinal part in a bit different light. So what we can do with some algebraic manipulation is to rewrite this longitudinal part into a different form, the current density times the vector potential. And this calculation I do not prove here because it's a bit tedious, but you can find it in the reference to the details if you want to check. So just applying some algebra and Maxwell equation, you can convert this form on the left into j dot a on the right, and both of these are 4 vectors. So now the interesting thing is that this j dot a is actually a well-known term in electromagnetism. It's called the interaction term of the electromagnetic Lagrangian density. So when people talk of the electromagnetic Lagrangian, similarly to what was presented to Jarek, then there are 2 parts. The first part is the field term that is describing the electromagnetic wave propagation, and the second part is called the interaction term. This J times A is describing the interaction of electromagnetic fields and charges. So this part is well known, but what is not well known before is that this interaction term is actually a longitudinal wave. And that is really what I want to emphasize here, because when we just start with the ordinary Maxwell equation and we have the current density part, well, we really don't know what that current is made of, what it really means geometrically. But with Giorgio Vassallo's approach, it's possible to identify that this interaction term, the J dot A, is really a longitudinal electromagnetic wave. And that is very important, as we'll see. So to see the significance of this result, let us apply it to the electron Zitterbewegung. And here I have a cross-section of the electron's particle aspect. Now the electron dimensions are measured experimentally, right? So we have the classical electron radius that's measured by scattering experiments, 2.82 femtometers. And then this gives one radius of the electron, and the other radius is the reduced Compton radius. So this is 386 femtometers, and this Compton radius is defining the electron's Zitterbewegung radius, right? So the electron's Zitterbewegung radius is a Zitterbewegung current, and this Zitterbewegung current generates the electron spin, which has a well-defined magnetic moment value, right? And so up to now, the big question was, what is really that current? How to understand this current? Why is it stable? And now in the following slides, I will show you some consequences when we understand that this current that we see appearing here is a longitudinal electromagnetic wave. So once we realize that, let us see what the consequences are. So the first consequence that we can study what happens when we look at the electron from a different reference frame, that is when we do a Lorentz transformation. So this wave going around on the left, it represents this longitudinal wave of the electron Zitterbewegung. And when we look at a wave from a boosted reference frame, then any wave is subject to the Doppler effect, right? So in this case, what we have to apply is the relativistic transversal Doppler effect. And this you can check when you do the calculation. This relativistic Doppler effect is shrinking by the gamma boost factor, the electron size along these x and y axes. Along the z-axis, we have the usual Lorentz contraction. So what this means is that when we are looking at the electron from a boosted reference frame and our boost factor is this gamma L, we see the electron size shrinking by gamma L. And here you can see it pictorially, that the electron Zitterbewegung, this dark blue, is in the rest frame, and then you can see how it looks like when we look at it from various reference frames. Now, why is this very important? It is important because we have a relativistic increase of the electron mass, and insofar as we consider electron mass to be electromagnetic field energy, then we have to explain why the electromagnetic field energy is increasing when we look at it from a boosted reference frame. And now you can see a very tangible physical meaning how it happens, that when the wave shrinks by the Doppler effect, the electric fields get more and more intense as you get closer to this shrunken size of the electron. So you can see a very tangible explanation that as the electron shrinks down, the electromagnetic field energy increases just as the fields get more intense at these shorter distances. So I think this is an important geometric result, because up to now it was really not clear why the relativistic electron mass should increase if the mass is comprising electromagnetic field energy. Okay, then the other consequence you can see when you look at the quantum mechanical waves. So let's consider again looking at the electron from a boosted reference frame, and the Lorentz boost is mixing the time components and the space components according to this matrix. And when you consider in the time component a wave oscillation with the frequency identified by de Broglie, then you can apply this Lorentz boost calculation, and by mixing the time component of this Zitterbewegung frequency into the space component, you can calculate what the corresponding wave number is. And so here I have this calculation. You can verify it. What you end up by following de Broglie hypothesis is that h bar times the wave number is exactly equal to the electron's momentum, kinetic momentum. So you can recognize that this is the basic postulate of quantum mechanics. However, in our case, it doesn't have to be a postulate. What we recognize here is that the appearing quantum mechanical wave is simply the Lorentz boosted component of the Zitterbewegung waves time component, right? So when we talk about a quantum mechanical wave, all we are looking at is just the Lorentz transformed component of the Zitterbewegung wave. So the quantum mechanical phase is the Zitterbewegung phase, but for all of this to make sense, the Zitterbewegung itself has to be some kind of a wave. And well, this result was known before, and because of this result, many people were considering Zitterbewegung to be some kind of a enclosed photon. But if you are talking about a photon, then it's not clear where is the charge coming from, because photon has no charge. But now that you consider the Zitterbewegung being actually a longitudinal wave, as I showed in the previous slide, it does define the charge. So you have both the Zitterbewegung charge current and the quantum mechanical wave. Okay. So now let's move on to the next topic and investigate the radiation that is given off by the electron. So when the electron changes its kinetic energy, then it gives off transversal electromagnetic radiation during its acceleration. So this I again showed geometrically what it means when the electron's kinetic energy is changing. It is a change in perpendicular direction to its Zitterbewegung plane. So you can consider emission of a transversal wave to be happening when the electron is accelerating in perpendicular direction to its Zitterbewegung plane. Okay, but what happens if there is some change in the Zitterbewegung plane itself, not perpendicular direction, but in the Zitterbewegung plane? So in other words, if the Zitterbewegung current could be converted to an electromagnetic wave, what kind of radiation would it be? So this question is tied to the question that Zitterbewegung critics often say, namely that if there is a Zitterbewegung current going around, then it should involve some kind of acceleration of charges, and accelerating charges should radiate. So what kind of radiation it is? Why don't we see that radiation? Where is the Zitterbewegung radiation? Okay, so let's consider if the Zitterbewegung could radiate, what kind of radiation it would give off. And the best analogy, I think, or the best example to look at is the muon electron decay. So the muon is considered to be an energetic electron, at least as a first approximation. You can think of a muon as a heavy electron. Why can we think of it that way? Firstly, a muon is always decaying into an electron. So the only way for muon to decay is for its Zitterbewegung structure to be changing into electron Zitterbewegung structure. And secondly, the muon's magnetic moment, again, to a first approximation, is just the mass-scaled version of the electron's magnetic moment. So this means that you give additional mass to the electron, you shrink down its Zitterbewegung current, and you end up with a particle that looks like a muon. And in case of a muon decay, that very, very tight muon Zitterbewegung, which has about 200 times smaller radius than electron Zitterbewegung, is gradually expanding until arriving at a stable position of being electron Zitterbewegung. So what is emitted during this decay? Well, experiments show that it's a neutrino wave that's being emitted. And as I showed in the preceding slides, insofar as we think of Zitterbewegung current as being a longitudinal electromagnetic wave, then it's quite logical that a radiative change of the longitudinal wave should give off some kind of a longitudinal electromagnetic radiation. So this suggests that neutrino could be nothing else but some kind of a trivial longitudinal wave solution to the Maxwell equation. And that is my opinion, that to understand what neutrinos really are, we have to look for the trivial longitudinal solutions to Maxwell equation. So trivial meaning some kind of a plane wave solution. The electron is, as Jarek was explaining, is obviously not a trivial solution because electron has a topology and electron has a very specific mass and charge value that is required for its stabilization. But the neutrino just propagates at light speed, and there is no reason why that could not be a trivial solution to Maxwell equation. Okay, so this now addresses the question of what Zitterbewegung radiation would look like, but it of course does not answer the question of why the electron does not radiate away its mass. So there has to be something that stabilizes this topology of the electron, and that is a big challenge to understand the electron stability conditions. Okay, so if you are interested to study more about the longitudinal wave solutions, I can recommend the book written together with my co-authors, Unified Field Theory and Occam's Razor. Many of the ideas I presented today are in that book, and also there are some of these longitudinal wave solutions calculated explicitly. But also you can do it as a homework, starting from the Lagrangian I showed you a few slides ago. Actually, you should be able to just calculate yourself what would be the trivial wave solutions of this longitudinal part. Okay, so now these are concluding remarks. So before this conference, there were a number of questions that were posed. And the idea of today's presentations, as I understand, is to answer these basic questions about electron Zitterbewegung. So first question, when we look at the elementary particle as the electron, what is actually circulating in the Zitterbewegung current? And my proposition in this presentation was that we are seeing a longitudinal electromagnetic wave that circulates at light speed. And this longitudinal wave creates the electron spin angular momentum. Okay, so what propels this periodic process? It is electromagnetic induction. And why does it maintain a constant frequency. Why it does not radiate? Well, it is obvious from what I showed in the previous slides that this longitudinal wave has to minimize the Lagrangian action, but beyond that, beyond this trivial statement, there is still some further geometric or topological condition to the stability that we have to understand. So, for example, Jarek's slides gave some ideas. Now, next question, it is often assumed that Zitterbewegung frequency is proportional to the mass. Is it true? And yes, in my opinion, Zitterbewegung frequency is proportional to the particle mass. And finally, does electron Zitterbewegung model apply to the proton? And again, the answer is yes. I have been studying this question, and I found that the proton can be described by analogous approach as the electron, but one important difference is that their Zitterbewegung topology is different. So that, in my view, electron-proton difference is just a Zitterbewegung topology difference. Okay, so that was my presentation. Thank you for the attention. I hope I'm doing well on time.
Thank you very much for a very nice talk. Okay, so we are past time, so maybe Adrian, I think he is here, so maybe Adrian can share, and maybe one to more questions could be asked in the meantime.
Yes, I am here. Could you hear? Can you hear me?
Yes. So please
yes.
share.
So fine. Maybe I have some technical troubles with my camera. I don't know what is what is wrong. However,
Can you share your slides?
yes. So I will share my slides. Can you see
Yes,
my
yes.
slides? Okay,
Yes.
so fine. Good afternoon to everybody. My name is Adrian Sulich, and I will give the talk about Electron and Zitterbewegung in David Hestenes model. I will try to reply for such a question, how to dismantle the antenna. Of course, it is a kind of a joke, because the problem of irradiation due to the Zitterbewegung in David Hestenes model is a very intensively discussed problem. And maybe some methodological remarks. Let's see the date with which I have written in this place. It is of course a mistake which is intentional, because nowadays, however, we have many new ideas and some on and theories, but we cannot understand, in fact, the internal physics of an electron and the quantum mechanics better than in these days. Oh, I don't know how to change the slide.
Oh, you have arrows and top left corner. Something is.
Oh, yes, I see, but something wrong is with the computer. Do you see my cursor?
Yes, that's we only see cursor, and there is some problem indeed.
Circulating, yes. I don't know why.
You can turn off the web browser and try to turn it on again. Restart the browser. But
Or restart the computer. It's up to you.
Maybe I will share again.
yes. It's the same.
The same. I don't know why, because it is a PDF file. So it should be good.
Or you can send somebody this file. For example, me, and I can switch if you want. You will talk, and I will switch if you want, but the cursor will not work. Or maybe the next person could present now, and you can restart your computer in the meantime. So maybe the next person, Mark, could you present now, and then Adrian should restart the computer and try to. Maybe you have okay. Can be like this. Sure. So there is some slideshow. Yes. Okay. Yeah. Sure. Should be like this. Yes.
Can you see these and can you hear me?
Yeah. Sure. Yes. So let Mark start and then Adrian's again.
All right. So indeed, we're going to go back in time, just like a time traveler who hasn't figured out how to use PowerPoint here, to before quantum mechanics took a weird turn. And I'm going to talk about the Zitterbewegung models, and we did a critical review of the models with the premise, as Einstein and Frank Wilczek would say, that to understand the electron is to understand the world. Oh, and of course, okay, so this is a paper we just published in the 100 years of Louis de Broglie matter waves. It's a special edition in symmetry. This is Olivier and myself. We're gonna show that we think all the particles Zitterbewegung models are interesting in the intuition they bring, however, fall short of factual match with what we observe about the electron. And we will reach the conclusion, as has been already hinted in the presentations before, that indeed we need to go back to a field model and also a fluid field model with the analogy of electrodynamics, Maxwell and Stokes. I'll talk about that. First, let's go back to the experiments, because we talk about radius of Compton, the radius of the electron. The truth is there are scales to the electron when we observe it. And the two seminal experiments, indeed pre-1925, Thomson scattering in the 19th century and Compton scattering around 1918. I have schematic representations. To the top left, you see the electrons are in the outer shell, so we can consider the electron arrests. The Compton scattering was inelastic, electrons were being emitted, whereas Thomson was a elastic scattering, represented here with the Feynman diagrams, where the momentum of the electron changes and the other doesn't change, and the momentum of the photon changes and doesn't change. Here is the schematics of the X-ray source. And that's what's of the Compton scattering. What's very interesting to me is that a low energy photon in Compton scattering is able to resolve the classical electron radius in a very physical way. This is a cross-section that comes out of the data from Thomson. So I find it interesting that a 10 to the minus 6 photon, a visible photon, is resolving a structure 10 to the minus 9 smaller. It's like saying, with my naked eyes, I can see an atom. How interesting. Compton increased the energy. Treatment is quantum relativistic, is the Klein-Nishina formula. And he arrived at the Compton wavelength. We talk about the reduced Compton radius, but really there are scales. And also what is interesting is if you go below 10 to the minus 15, there are no further scales at 10 to the minus 18. At CERN, for example, we see no further structure to the electron. And also very interesting is that the two structures that we know, from the scale of Fermi, the classical electron radius, to the scale of Compton, to the scale of Bohr, each time we have a factor of alpha, the fine structure constant, indicating an electromagnetic interaction. I will come back to that. All the blah, blah, blah with the math that we love so much, but to say that all of this derives from the Dirac equation, where Dirac, if you look closely, and Olivier will talk about that in more detail. So I also, even though I have a theoretical physics PhD, I fucking hate the math these days. I can't take theory anymore. I just want experiments. But just to point out that in Dirac, we do have the movement of an electron and a Zitterbewegung movement of something at the scale of Compton, 10 to the minus 13, 10 to the minus 12 meters, moving at the speed of light. These are the known facts about the electron directly sped out from ChatGPT. I love the AIs because whenever they tell the same thing, we know we have the common denominator of what is known. I think the AIs hallucinate just like a lot of us here. But when it comes to known and replicated facts, they're great. So what do we have? We have that the mass is 511, has an electric charge, it has a spin, has a magnetic moment, it has a Landé J factor that is anomalous. It has a Compton scale, it has a classical scale, those two scales I just pointed out from experiment. It has a de Broglie wavelength. Now, what's interesting is that the de Broglie wavelength is not an intrinsic property of the electron, it's a property from the observer, okay? Because it includes this momentum that is not an intrinsic property of the electron, but rather the movement of an electron in a reference frame. We know an antiparticle about it. What's very interesting also is the stability of this thing. This thing is extremely stable. The electron is probably one of the most known stable particles. And I stress that because, well, we'll talk about it again in the context of superstable orbits. Speaking of time travelers, let's go back to 1918. This is Compton himself before he gets his Nobel Prize. And he says, guys, I've looked at my data and my data says it's not a point, because if you ask anybody nowadays, will tell you it's a point that has all these properties that we don't understand. But Compton himself, in a very great article, it's actually from Olivier, that gave me that reference recently. It says it's a ring. It's a ring of current at the scale of, he shows here what we now call the Compton wavelength, the 2.310 to the minus 12 meters. And also he says, and this is correct because the Foreman's effect that he describes is when he changed the spin compared to he could see different diffractions. I'll come back to that, but in all the slides we've seen, for example, even in Andras' presentation, the movement of the spin is collinear to the propagation. There's no reason for that to be. In fact, we know it is not a fact. The spin can be in any direction. That's even from Stern-Gerlach. The spin up, spin down on a vertical propagation. But he says, guys, it's a ring. Okay, so what we've seen lately is a lot of models in the Zitter, and Olivier, Andras, and I are all part of the Zitter Institute, and Hestenes is there, and all these guys, and Konza is one model. So we have a ring, and it incorporates these two scales we talk about. The little r here is the Fermi scale, 10 to the minus 15 meters. And the big radius is the Compton scale. Of course, this is not at scale since the ratio between the two is the fine structure constant, 137. But this is schematic, and it says, let's consider a thing that is moving with this topology. Great. We have particles, we have electrons in there. Olivier Konza is a professor of electromagnetism, I think in Barcelona. So when you have a hammer, everything looks like a nail. And so Olivier thinks about the electron as this antenna, fair enough. And he derives very interesting results. Another model that we've studied quite in detail is that of Giorgio Vassallo and Andras. And in there, we have a little ball of a particle that is moving at the Compton radius. And the size of this little ball is the 10 to the minus 15. So again, ontologically, the same building bricks. And it's moving at the speed of light. And notice this very interesting self-oscillation, oscillation of the ball on itself, which corresponds to the external oscillation. And that's the model they have. And they derive quite a few results with this models, all great. One of my personal favorites, because I've spent almost 2 years on Martin's models, and Martin is also a member of the Zitter group and an emeritus academic now, and he's written his opus magnum called the kinetic theory of spinning particles, and in his model, you have a point particle that is moving at the speed of light in the reference frame at the Compton's distance. And he also, just like Vassallo and Andras did, parachutes an internal spin so that he gets the right results when he quantizes, quote unquote. And these are great, but there's a couple problems. One is that with these particle models, we never arrive at the proper spin angular momentum. There's a factor of 2 that's always missing. The spin is never quite right, so that we have to hypothesize. In the case of Martin, he just parachutes the intrinsic spin. And, you know, as a physicist who's done theoretical physics, and my PhD was on weird stationary modes of Maxwell's equations called Bessel, the Bessel solution to Maxwell's equation. At the time, it was a world first, not to brag, but that's what I did. You know, I'm familiar with, look, we have these electromagnetic waves and they do things, but I want visualization of quantum. I was taught by Alain Aspect at the Polytechnique moons ago in the 90s. And, you know, yeah, I know the story. Nobody needs to yell the orthodoxy in my ear. I'm here as a retired entrepreneur now to understand what the hell is going on and where the fuck did we go wrong in the visualizations. And so if I have to go through all these models and at the end postulate yet another intrinsic spin, you're wasting my time, basically. And so, you know, that really is my take. It's not a criticism, but, you know, Rivas is clear about the fact that the spin Compton movement is not necessarily the same as the displacement of what we call the electron, which would be this composite wave. And so when we see diagrams like we've seen before, where it's always collinear, there's no reason for that to be. So that's the bad news. The good news, you know, and there are many good news, don't get me wrong, there's many, we spent years on it, not because we wanted to prove it wrong, but because there's very interesting insights, even into QED, as we'll see in a second. Namely here, this is Rivas's model, and you can see on the left an electron with a spin going left, almost at the speed of light, they're 120 keV, so mildly relativistic electrons. And Mott scattering is an observed fact, and within the model of Rivas, again, Rivas allows for the spin to be here perpendicular to the plane of the page, whereas the movement of the electron is in the page. And when we do that, we see this weird cycloid form, right? Because we're going at the speed of light, and the electron is going at the speed of light here in red, and the charge in blue is also going at the speed of light. So we have a cycloid forming, and that's enough to explain the asymmetry of the scattering. Also here, what I call the Egyptian Eye of Ra is a semi-stable orbit for a while. These are dynamic systems. In the case of Rivas, he has dynamic equations for the electron, which I really like. And you see this semi-stable thing that wants to appear and then gets out in the proper Mott scattering angle. And that's very interesting to me because Mott scattering in standard orthodox, so to speak, quantum mechanics or QED is a fairly complicated calculation. I mean, you have 10 steps and the B field relativistic is E and blah and blah. I mean, quantum mechanics has to go through the usual contortions to explain this fact of nature that we see. I'm always reminded and meditate often on the Ptolemaios model where, hey, we could explain the motion of the stars with a very complicated math model. And in fact, to me, the lesson is that we can always torture our math to say whatever the F we want it to say. Doesn't make it right. And in fact, we'll try and burn somebody just because they piss people off. You know, when they say, hey, guys, maybe there's a simpler explanation than the geocentric or heliocentric model of the stars. So never mistake the models, but this is interesting. The other thing that's interesting is the G2 anomaly. And this is true of most of the models. So for those who are mildly familiar, one of the quintessential proof of QED is this claim that we're precise at 13 digits when we measure the G2 anomaly in experiments. QED models the G2 anomaly as an expansion of the fine structure constant divided by pi. And the great claim of QED is the Feynman diagrams that describe these things actually replicate very well the -13. But one of the things that attracted me to Professor Konza and the Zitter group is that he wrote a very provoking pamphlet called Something is Rotten in the State of QED, where he shows the history of how the formulas and how the experiments kind of chased each other's tail, justifying each other. But it's one of those, we don't really know historically where we went wrong. Uniformly across most of them, not all, but most of the models of the Zitter we've seen, Konza, Vassallo, everybody again tortures their model to get into alpha over 2 pi. And in first approximation finds this factor that is called the Schwinger factor. And this gives us a precision of 5 digits. All right, well, that's not bad. It's also very geometrical in most cases. And the way I read it is, well, if the magnetic moment is in fact this surface current, this current around the surface, and we correct the surface with a small Fermi scale alpha over pi correction, then yes, I can see how I could go about trying to torture my math into saying the right thing, which they all do. Now, this is meant as a criticism. Of course, had this result not been known in advance, I very doubt any of these gentlemen would have found the right solution. So it's one of those cases where we know what we need to land on, and therefore, I don't mean it that way, but I do, we cheat our way to the answer, which is fine and good. But again, the message here is that the ingredients, this Fermi scale correction to a Compton orbit, may be enough to, may be a way to go about explaining even the anomalous moment. And this is a visualization of the prize crown jewel of achievement of QED, which is nowhere to be seen when we talk about Feynman diagrams. I'll say this, and he probably will stop talking to me as a result, but Professor Cvitanovic, who's professor here at Georgia Tech in Atlanta and is a specialist of chaos theory and G2 correction of Feynman diagrams, when I presented this, the exact words out of his mouth, and he will never put it in writing, are, I can't wait for you guys to do away with these stupid Feynman diagrams. And this is one of the world experts on Feynman diagrams. We've touched on this, and I'll repeat how we reach the same conclusion of cells, namely that it can't be particles. Yes, the particles are great for our intuition. Yes, we arrive at interesting results when we consider the particle models, but no, it cannot be a particle. It must be a field. And when Jarek, bashes us over the head with all his diagrams, he is talking about topological singularities of field. Field, a topological charge. And here I'm going to introduce what's a topological charge. First of all, and it's in the paper, the problem with a particle is it cannot be a point particle, because how the hell does a point have properties? I mean, philosophically, it's a stupidity. We know that. And we just say, well, it's an approximation. We assign those properties to the point, just like in Newtonian dynamics. No, the Earth is not a point, but the movement of Earth is well approximated by a point. But then, unlike the Earth, it cannot be a distributed charge, because a static distributed little ball like Vassallo, as here, should undergo Coulomb repulsion. In fact, rather strong Coulomb repulsion. The charges should fly apart. This, by the way, is historically what stopped Bohr in his tracks when he tried to model this. And the only way to reconcile this apparent paradox is to say that charge is not an ontological thing. It's not a real thing. It's a dynamic field property. And so let's go there for a second. Here are examples of topological charges. Here you see a field that has a non-null rotational. Here you see a field that has a non-null divergence, etc., etc. And so I propose to everybody as a meditation, and do it outside of this conference, but really sit down for a second and think about the way we've been taught electromagnetism. We put a charge, the charge moves, and the acceleration of the charge gives us a field. And therefore, we call it a source, by the way. And so the way we are brainwashed linguistically into understanding Maxwell's equation is with the causality of a charge moves and gives us a field. But there's a perfectly equivalent, mathematically speaking, way of understanding Maxwell's equation, which reverses this understanding of the world, which says, let's assume that there's only a field of something, which we'll get into a second what that is, hint, hint. And if that field moves in this way, then we can see that here we can calculate, when I calculate the divergence of the field within this ball, I will have a non-null scalar within the ball. Let's call this the charge. But this is a topological charge. It is not an ontological charge. We don't put the charge there. We just have the movement of a field, and when we calculate the divergence, I have a scalar. But there only is a field. And that's the only way to reconcile all of this. All well and good. So there's a few models that I've tried to do that we reviewed. Number one, and I have 10 minutes left. Number one, Carlos dos Santos, one of my favorite professor of physics in Brazil, spent a lot of time on his papers. Unfortunately, the man cannot speak English for the life of him and refuses to use AI, so his work remains a little bit throttled that way. But here you see a wave, which is interesting because it's an E and a B wave. And it's not readily apparent, but you look very closely, there's something very particular about this wave in that it is left-handed. It is not a right-handed normal plane wave. It is this weird esoteric left wave. And then when he does it left wave, number one, he finds that the Lorentz force that results is unable to stabilize this thing. Again, he puts a torus at the distance of Fermi, that's the Fermi distance here, around the Compton vector, around the Compton radius circulation. And so this left-handed EM wave goes into this stable orbit as a charge, which he calculates by integrating the divergence of the field over this geometry that is close to 1, meaning E. So hey, what an interesting little model. The guy goes, postulates a field that is non-classical. We're not talking about a classical right-handed EB plane wave here. We're talking about this weird left-handed wave that finds its own stabilization. One of our personal favorites, even though it's a lot of cheating through diagrams and doesn't mean anything in reality, is the Williamson and van der Mark tricycle model that's made a lot of noise for the past 20 years. Well, they say, hey, if we put a B and an E field on I don't know what that belt means physically, like as a Maxwell specialist, I don't know what that means. What's a field only defined on a 2D surface? A field is a 3D thing. But in any case, I understand it as a phase. And if we consider that the phase of this hypothetical field takes 2 turns to come back onto itself, so a weird left-handed wave again that lands back onto itself after 4 pi, we find a lot of the facts that we are looking for. Namely, we find the proper Zitter frequency, which none of the models we have studied finds. We find the proper spin, which none of the models by a factor of 2 found. We find the correct Landé factor, the anomalous, not anomalous here, just the -2 from Dirac, et cetera, et cetera. There's a lot of problems with it. We're not here to criticize for 10 hours. So let's move on. Back to Compton. On the left, we've seen this diagram in Andras's presentation. Again, here the plane of oscillation at Compton is assumed to be collinear with the propagation. There's absolutely no reason that would be the general case. In fact, the general case is here with Rivas. In here, the plane of oscillation is in the page, therefore the spin vector is perpendicular pointing to you, gentlemen. And when we accelerate relativistically from 10 keV to 100 keV, meaning we are looking at Mott scattering or the scale of Mott scattering, we see these cycloids that are very interesting. And again, that's enough to explain Mott. In the case of Kanza, we have this helix without deformation. In the case of Carlos, we have no deformation. We just move at the speed of light. And so nobody agrees. Olivier will talk briefly in his presentation about the gamma square dependency, depending on whether we're going collinear or perpendicular. You know, so these thoughts are interesting. But here's our thought, and I'm discussing that with one of my experimental mentors. Actually, next week, I'm going to the University of Nebraska, presenting this to the faculty and sitting down for 3 days with Herman. Could we redo Compton with modern accelerators and modern detectors? Because if Compton says, hey, we depend on the cross-section or apparent cross-section of the electron at rest, remember that Compton experimentally was scattering of valence electrons, number one. And number two, that the model with which they arrive at Klanishina assumes that the electron is at rest. But if there is a gamma dependency, which in the case of 100 keV is about, you know, we can go up to gamma 100. And if we have a gamma square dependency, then there should be a variation in the effective cross-section. Is that enough to measure a deviation in the wavelength that the Compton effect shows? You know, that's one way of attacking this. This is from John Macken, who's presenting later, and I just took it from his presentation. But again, this very interesting de Broglie wavelength. And again, very interestingly, not an intrinsic property of the electron, but an extrinsic property of the electron. Meaning, it depends on the observer and us moving through a framework. And this was also understood by de Broglie. We have modern treatments on this that say, well, if we presuppose a standing wave at the Compton wavelength, right? We talk about, is my electron an antenna? Well, the first field antenna would be a standing wave, or actually the second after the traveling wave. And if we have a standing wave, what's interesting is you can always understand a standing wave.
Are you looking at it right now?
No.
What's
They
that?
have you saying on the screen, this guy, Marc Fleury or whatever, has your images on the screen. He's talking about them.
Great, thank you.
Okay.
I'm sorry.
Yes. And going outwards, this was de Broglie, by the way. John makes a great, with his son, great images that I love, so that's why I use it, and this is with permission by John. But in essence, the outward propagating would get, if the thing is moving to the right, it would get compressed, Doppler shift, expanded, and when we sum them back on the Doppler shift in and out, we obtain a beating. And now this is what is very interesting, and was de Broglie's starting point, actually my starting point into the Zitter, is that if and only if, okay, this is a logical equivalence. If and only if, which makes it a very interesting epistemological point. If and only if the standing wave is at Compton, do we obtain a beating at de Broglie? All right? Only if we have Compton in the standing wave do we see de Broglie as a resulting wavelength. This was already understood by Louis de Broglie. Okay, but then it begs the question, all right, so we have this thing we call the electron, which seems to be a field, and we'll talk about the analogy of hydrodynamics. Andras already touched upon it, which is why, as Eleanor Capital, we focus on these themes. And what's interesting is in 1951, Dirac himself, all right, writes to Nature and go, guys, it's gotta be an ether, all right? It's gotta be an ether. And this is Dirac, he's already a Nobel Prize, Cambridge, blah, blah, blah. And of course, the editors, you know, feel the need to say, the editors do not hold themselves responsible for the opinion of their correspondents, and blah, blah, blah. So the ether is taboo, but Dirac himself says it's an ether. I will not talk about this slide, one, because my time is running out, and number two, because Olivier, this comes from Olivier, and he'll talk in detail about this. But there is a perfect formal analogy between Maxwell and Navier-Stokes. And one of the interesting historical facts is that actually Stokes was the mentor of Maxwell at Cambridge. All right, Stokes reviewed the early forms of Maxwell equations. This has been revisited many times. I won't go into details, but just to quote this apple shape, and that it's a weird ring shape thing that is moving in a fluid. And so where we would have a Fermi scale. And so just because I'm running out of time, I'll just leave you with this idea, which is where we're working now, which is what's interesting is when we collide electrons and positrons every day, we obtain photons, and this we measure every second in industry. It's, you know, that's medicine, that's PET, scanners, and, you know, they're everywhere. But when we inverse this arrow and saying, but what if we took two photons and made them spin about each other? Could we get electrons? When you say that, people look at you like you're crazy. But indeed, our hypothesis right now is that a photon, which we don't really know what that is, just a field excitation, for some reason finds a self-oscillation, interacting with itself, forming a superstable from nonlinear chaotic dynamics orbit at Fermi that traps the energy in indeed the classical radius, which gives us the mass of the electron. So in this image, the mass is indeed, as Vassallo, Hestenes, everybody says, is indeed an electromagnetic energy. So the equivalence of energy and mass is here exact, but it's electromagnetic. Okay, so Einstein was correct in this, or rather, this is pretentious. Excuse me, this is a way of understanding Einstein's dictum. The charge is also emergent at Fermi, 10 minus 15. The charge is an emergent property of a field going into a turbulent motion of a vortex, just like a fluid of Navier-Stokes does. So charge and mass are emergent. And the spin is the second orbit at Compton. And this would be a Bohr orbit. Little point of interest, experimentally, the ratio between Fermi and Compton is exactly 137, the fine structure constant, and the ratio between Compton and Bohr is also exactly the fine structure constant. The second appearance of alpha is trivially understood as the electromagnetic interaction of an electron with the protons, therefore the force, and therefore alpha, because alpha, as you know, is the square root of E. It characterizes the strength of the electromagnetic field. And the fact that we have alpha between Fermi and Compton, in my opinion, justifies that everything we've been talking about is indeed an electromagnetic self-interaction. So that the electron-positron annihilation reverse would say, what is matter? Matter is trapped light, which for those who are also versed in esoteric religion, the birth of matter is in fact the Ouroboros of the Egyptians, light chasing itself and descending into materialism. These are the Luciferians, those who bring the light into trapped form. All right, and I'm done, and I will just ask for a second of semi-silence and look at a thing that the dolphins do, and now they go back to the little small ones, the muon, and it grows back into a big one, and it's stable, and they go back to the little one, and it grows back into the electron. And the dolphins play with that stuff, and that's it.
Thank you very much. So we have time for one short question. So I could ask why the charge is quantized again. So
So the charge is quantized because in chaotic dynamics, this is against Zvitanovich, whenever you confine a system, say a Lorentz weather system, the nonlinear equations say the orbits are in fact going to be discrete. You do not have a continuum of stable orbits. And so the quantization in here appears very naturally, in fact, as a byproduct of a superstable self-oscillation. All right, this is a direct consequence of chaos dynamics. And when I asked point blank the question to Predrag Zvitanovich, I said, come on, man, you did your PhD on G2 anomaly. You spent your life, he's 80 years old, and he still teaches in spandex, field theory and chaos theory. You know, I attended his class. I love the man. And I said, come on, you had to have put the two together from the beginning, that in fact, the quantum mechanics and the electron is a turbulent self-oscillation of a super stable cycle. And he goes, yes, of course, this is where I started. You know, and so I think problem is we have taboo because it's an ether. We are talking about an ether here, and that's taboo. And so at the end of the day, I want an experiment. This is all nice and you know, but we're in the Tower of Babel, pun intended, B-A-B-B-L-E, we tell stories. But we're all hinting at the same reality and we need experiments. And so that's what I'm discussing now. I put Andras, I put Olivier, everybody's on. Can we do something with redoing Compton and proving something instead of blah, blah, blah all the time? Also linked to cold fusion, just as a way of shocking even more people. But the funds come from LENR Capital. That's it.
Thank you. So, okay, so we are out of time. So maybe Adrian could try to share again.
Yes, I will.
Okay, thank you.
But I don't. I cannot see it. I will try to start it again. Yes.
To either the simplest solution to talk with people is just use electromagnetic field, which only lacks the charge quantization. So we need to add built-in charge quantization to Gauss law, and we have not ether but just fields, electromagnetic fields. Okay, I think it's okay.
Could you tell me something about this technical issue? Can you see my presentation?
Yes. We can
Yes. Okay. So, so let's try to continue it. So as I told you, the topic of my presentation is Electron and Zitterbewegung in David Hestenes model, and it will concern how to dismantle the antenna. Firstly, I will tell you something about the Electron and Zitterbewegung in David Hestenes model. However, it will be only a formality because I suppose everybody knows it very good. The figure is from the Zitter Institute webpage, and it is with the permission of Professor David Hestenes. Thank you, Marc, once again for asking on my behalf Professor Hestenes to obtain this permission. In his famous work, Professor David Hestenes written that there is some hidden geometry in the Dirac theory of an electron. And the illustration of this geometry is in this figure. There is an electron is a point which is traveling along the helical path, and the imaginary unit, well-known imaginary unit which is present in the Dirac theory is generator, in fact, generator of rotations. And the radius of it is like that, which in this equation. with other kind of notation, because I prefer it, because my hypothesis is that an electron has no stable and constant radius, and it depends on many factors. The Zitterbewegung is an angular velocity of the point, and the linear velocity of this point, I mean this velocity, is the same like the velocity of light in a vacuum. However, some critical remarks are done by some people that this kind of an electron, point-like electron traveling along a helix, would be a circular antenna, like in this figure. And there is also another kind of problems. I mean, the structure, such kind of a structure would be very highly symmetrical. So that means that it should be a boson, because there is no factors which could determine this its fermionic properties. However, on the other side, space-time algebra is space-time algebra. So Professor David Hestenes could not do any mistake. And this kind of geometry, I suppose, is correct. Moreover, there are some forgotten studies about an electron, talking to us that an electron is a ring. And some of these works were presented by Marc Fleury. I mean, for example, the Compton's work and so on. So there are some experimental evidences as well as logical and geometrical that in favor of the hypothesis that an electron is a ring. So maybe the question is not if the helical path is correct, but what is really the point moving at the velocity of light. The velocity of light. And some hint is, as I think, this velocity, because the only confirmed object in nature moving at the velocity of light in vacuum is, of course, photon. So the model I will present is based on the well-known idea that an electron is something like twisted photon. And it is worthy to say also that there are some other arguments in favor of this conception. I mean, for example, some old works made by Darwin, who told that the mathematical formalism used for photons should be also used for electrons and matter and so on, due to the similarities. I mean, the duality of matter. Another hint is the fact that electrons and positrons are created at strong electromagnetic field, and they are created from high energy photons, which are crushed, like it is illustrated in this picture. And to the best of the university knowledge, I mean the usual school knowledge, there is some magic process which creates an electron and a positron. However, it is not known what is the mechanism of it. However, it is significant that the matter of electrons and positrons are photons. And there is also another hint. I mean the fact that electromagnetic wave can be bent at the Schwinger limit in the strong electric field. So it is possible that during this process, the same process of bending of electromagnetic wave occurs. The second hint is the fact that there are some mathematical equations, mathematical relations between the parent photon momentum and the quantum radius of an electron. This radius of an electron is, of course, calculated by Professor David Hestenes. However, I would like to present another way of calculating it, because it is very significant. So let's look. The angular, this part of the equation is the well-known spin, which is angular momentum of an electron treated as intrinsic. However, I think it is not true. It is not a magic intrinsic property of an electron, but something which is coming from the photon momentum. So the photon momentum is this, and there is the radius of an electron, the quantum radius. And when we transform this equation using the energy of photons, we obtain such equality from the law of energy conservation during the Zitter creation, the Zitter electron positron. And from this, we can obtain the radius, which is present in the Dirac's equation and was noticed and described by Professor David Hestenes. The obvious conclusion is like that it is a circularly traveling photon. And as you can see in this picture, we have a specific topology which create the so-called church. I use the transformed Gauss law with this sign to show you that maybe the church is not this unknown ugly substance which is taught at school as the church, but it is this is simply the electric field. And this model predict it. And as we can see, the same oscillation, I mean with the same sign of oscillation, are always in the same external or internal part of this geometric structure. And of course, the positron is circulating in the opposite side, and the church is opposite. So it shows us also what are the differences between matter and antimatter, and that is something, the matter or antimatter is something relative. However, we don't know how many half of the wavelengths are placed inside of this, and it will be the topic of my next slide. Because as you have noticed, this kind of structure would be also a boson, because when it is circulating, it doesn't matter from which point we will start. We obtain, after one circumference, exactly the same topology of the field. However, when we use not odd number but even number, we obtain another situation like that. For example, for the 5, we obtain this structure, and for 3 phases we obtain this structure, and so on. And now we can calculate the exact value of this. I mean, the quantum circumference of an electron and the parent photon wavelength should be compared to obtain the correct value of the numbers of the phase. And when we compare the quantum circumference of an electron and the parent photon wavelength, we can see that only and exactly 1/2 of the wavelength of the parent photon is in the quantum circumference of an electron. And the same discovery has been made previously by Williamson and other investigators. So we can situation like that. because it is 1/2 of the wavelength. So we have two phases of the oscillation of an electron, of this photon. This is the plus because there are the opposite phase of the oscillation, and this is the minus. However, it is arbitrary if the field is maximum or minimum, because we cannot check it experimentally. However, the main important fact is that they are opposite. And where is the electric dipole moment? There is also another important question, because the electric dipole moment of an electron is now assumed as to be parallel to the spin. However, as we can see, the spin is in this plane and in this direction, but the electric dipole moment is growing from the asymmetry of the electric field is placed rather in this plane, perpendicular to the spin. And similar discovery was made by Martin Rivas and described in his work. However, it was from another kind of analysis, but the conclusion is exactly the same. And what about the anomalous, so-called anomalous gyromagnetic factor of an electron? Let's look. When the electromagnetic field is oscillating like this, we have also some opposite phases of the magnetic field created perpendicularly to this. And however, the vectors are in the opposite directions, but as we can notice, the phases are also opposite, so they both works as a dipole, like a dipole. So
okay, so
they
I'm
are
moving into the dining room.
Okay.
Are you going to need?
Go ahead. I just had to mute John.
Yes. So they all can be summed, and it gives the gyromagnetic factor 2. 1/2 of this oscillation and the magnetic moment can be easily calculated from this simple equation. And now also we can see what is the so-called spin quantization mechanism, because I told so-called because it is in fact the quantization of the direction of the magnetic moment of an electron. And now we can see it very clearly in easy way, because it is similar to the toy. I mean, I don't know how to say in English, how to name this kind of toy, but it is a simple toy which is circulating, and when an electron is placed in an external magnetic field, and we have oscillating phases of this also circulate, and that is the mechanism of this quantization. But now it is the time for the titular question, how to dismantle the antenna. So look, it is an electron at rest. However, we have a circulating wavefront clearly visible in this, and we have oscillating electric fields in this plane. There is no movement of the maxima. There is also oscillating plus minus, and so on. So it is quasi-standing wave. I use the term quasi-standing wave because of course it is not the traditional linear standing wave, which is well known from the textbook for students, but it does work in exactly the same way. And when the electron is at movement, I mean, thus in this in this direction, we have two components of this. Standing components in the Zitterbewegung plane and traveling components, which is perpendicular to it. So only these traveling components, in fact, can emit radiation, not this. This is not an antenna. So an electron at rest, despite of the Zitterbewegung, is not the circular antenna. And now we should consider the nature of an electron's movement and its consequences. I mean the fundamental consequences for everything, for quantum mechanics and so on. Firstly, the direction and velocity of the wave. So let's look. This kind of linear photon is also traveling with at the velocity space at the luminal velocity. However, massive particles cannot obtain this velocity simply because firstly, they have some electromagnetic field which gives them mass, but there is also another component. Let's look at this at this way. It is longer than this distance, so even if the particle has no charge, it would have some additional mass as well. And of course, the direction of the traveling electron cannot be straight. It is not a ball like macroscopic ball, which can travel straightly along along the force which forced its movement, but the direction of the movement is always quantized. And the next consequence of the nature of an electron movement is, as I told you, the mass. And so we have two components of the mass. One is electromagnetic, and the second part is growing from this kind of movement. And it is probably hidden in this well-known from the general relativity theory, so-called Lorentz factor. Another consequences of the nature of an electron movements is so-called chirality and helicity of particles, because we can now see it in this figure very easily when it is moving in the opposite side, opposite direction to the spin. It has another helicity than in this case, and I suppose chirality should be something closely connected with this. However, I have not investigated it yet very carefully, so it is now only some kind of a hint. And now let's think about so-called electron radius measurements. What we measure indeed when the electron is traveling at high speed and it is colliding with other particles and so on, so-called shortening of this distance occurs, and there is also another changing of the radius. I mean, connected with the Broglie dependence between the wavelength and the angular momentum, because it is in this plane. So two kinds of the changing of the electron size occurs, and as I told you, I suppose that an electron has no constant radius, and it is very highly dynamical structure. So maybe let's go to some conclusions. Firstly, a preliminary toy model of an electron based on meta-analysis of other models and experimental data was proposed. And it is consistent with Zitterbewegung interpretation of the quantum mechanics proposed by Professor David Hestenes. And it was shown that Zitterbewegung in that model does not cause emitting electromagnetic waves. This model could be a starting point to understand more deeply the quantum mechanics because it gives us some very easy to understand picture of the quantum mechanics. So it has some didactic value maybe. The model predicts many known properties of an electron as well as some new phenomena to be checked. I mean, there also could occur some particles isomers. I mean, made of left-handed or right-handed photons. Of course, it needs to be more deeply researched, but I have such idea for the future research. And these electron isomers, as well as opposite helicities and chiralities, could have different spintronic properties. As well as there could be some electrons and positrons isomers which could not annihilate. And there are some also more general ideas, I mean more philosophical. And so let's look for this philosopher, Democritus, which was born before Christ. And he told us that nothing exists except atoms and space. Everything else is opinion. I think now we can say that nothing exists except electromagnetic wave and space-time, and everything else is opinion. And look at the time when this was thought. It was before Christ, and the discovery of atoms was done after 2000 years. So maybe this kind of reflection, I mean philosophical, not only mathematical, is only a very important thing in physics, especially that that now physics suffer from lack of it due to the known shut up and calculate rule. So instead of that, I think it would be good to say rather think everywhere and about everything, also about the most forbidden internal electron physics. So thank you for your attention.
Okay, thank you very much. So there's the time for one brief question again. So again, I would ask why
Maybe I have a comment. First of all, I really enjoyed the presentation. Second, in the event that we're talking about an ether and the fluid movements of the ether and a topological charge, let's not forget that the antenna is when what we call the electron is accelerated. But in our new picture, the electron is the composite structure. And what we call the charge is this field singularity. And what I'm getting at is I think there may be a philosophical miscategory by applying Maxwell to this fundamental charge, which is fictitious in our case, because it's a field that's doing a thing, and the second order of that thing, Fermi plus Compton, that we call the ring electron. And it's when that structure is accelerated that we see a radiating antenna. And so I'm just, you know, whenever I appreciate the effort of the antenna. I know many people take this very seriously, and absorption, reabsorption, and the stability and the orbits and da-da-da. But, you know, it strikes me that, wait a minute, maybe we're imposing, so it's a miscategory. Maybe we're imposing, what about the radiation if our charge is doing that at Fermi? When the answer is, well, what we really know experimentally is when the composite Compton structure is accelerated, only then do we have an emission of a field. And, making conclusions based on macro Maxwell to the micro Fermi structure may be premature. I'll just put that out there for you. Otherwise, I really enjoyed the presentation. Thank you. You seem to be channeling Williamson very clearly.
I just have a question, maybe, for Adrian. So you said in your presentation that the de Broglie wavelength is a transverse radius of your helix, no? This is what you said?
Excuse me, could you repeat the question, because I don't hear it good.
Okay. So when you mention your helix, when you have a motion, you have an helix, and you said that the wavelength, de Broglie wavelength, is the transverse radius of your motion, no? No, maybe not. Don't worry. It was in your previous figure, but don't worry. Okay. If you come back before, yes, this one.
This
After?
one?
No, after.
Yes.
After. This one here. You see that.
Yes.
How do you interpret the de Broglie wavelength? Is it the transverse radius?
Yes, I interpret the de Broglie wavelength as the wavelength which is exactly equal to the circumference of the Zitterbewegung. However, I should rather write it 1/2 wavelength. However, it is connected with the plane of Zitterbewegung motion. So one wave, two circumference, and a half of wavelength, one circumference. Because it is, let's look, the momentum is non-zero, so it can be applied only for electrons which are traveling, not at rest. Not at
Yes,
rest.
but the formula, if you have a formula, it should be valid also at rest. Huh? And when you are at rest, your wavelength is infinite. So if you have a formula, it should be available. It should be applied at rest or in motion. And here, at rest, your wavelength is infinite. So I'm not convinced.
At rest, so it is not applicable to the electron at rest, because it would be infinity. It is not for electrons at rest. Only for traveling.
Okay. Thank you.
Okay, so then, Olivier, I think you can share your screen and.
Yes. So hello everyone. I will just share my screen. There is yeah.
Could you stop sharing, Adrian?
Yes, yes, to stop sharing.
Yes, Adrian, we need you to stop. There you go. Thank you.
Thank you. So you see my screen or no?
Yes.
Okay. Thank you. So hello everyone. Maybe I put it in full screen. So just to introduce myself, so initially I have a PhD in quantum physics at Sorbonne University. I worked a bit at CERN, in Geneva, and I am very interested in the thematics in the electron, Zitterbewegung, realistic approach in quantum mechanics. Currently, I worked as part of the foundation of Marc, so LNR Capital Foundation. And here in this talk, I will talk you more about the analysis of the Zitterbewegung equation and the Dirac equation. This comes from the fact that I am very surprised that among the people that study Zitterbewegung, only not a very few people really study that what are called the Zitterbewegung equation. Most of the people talk about Hestenes, but very few people talk about really the Zitterbewegung equation that Schrödinger derived. And for me, it should be really the starting point when you study the electron. So that's why I wanted to talk to you about that. And behind this, thanks to the Zitterbewegung equation, you can understand better what is behind the Dirac equation. Okay, so to derive the Zitterbewegung equation, basically you start from the Dirac equation. So it is here the Dirac Hamiltonian. You have those two factors, beta MC squared and the impulsion factor. Alpha is the Dirac matrix, so 4x4 Dirac matrices. You have those two formulations in terms of alpha or in terms of the gamma matrices. Okay, so you have three matrices, one per spatial component. I will not do the derivation because it's quite long, but this is what Schrödinger did in his famous article of 1930. So he went through the Heisenberg picture when the derivative, time derivative of an operator is I divided by h bar commutator Hamiltonian operator. And he got what are called the equation of motion of the Dirac particle with the equation of the position operator. When I put a hat, it's an operator. So K is just the index of the spatial index, so it's 1, 2, or 3. You see that the X component position operator can be decomposed into two components. The component of the center of mass, so it is called Cm for center of mass, and the oscillatory component that is called Zitterbewegung, ZBW. Okay, so you have it for the position operator. You have the same for the velocity operator, which is derivative of the position. You have those two components of the center of mass and also oscillatory components. I will analyze those two components after, but this is just to mention that here, at first look, you see that for the velocity, you have a constant term, c squared p divided by the energy, just the relativistic velocity. And you have this oscillatory component that is called the Zitterbewegung component. Okay. Here, all those results were derived from Schrödinger. I truly invite you to have a look at the historical paper of Schrödinger. It is in German, but here it is a translation in English. And it is quite technical, but very useful. And you see here, you have the equation I mentioned you. So X, you can decompose to the uniform longitudinal propagation, and also zeta, it is called here, you have this oscillatory part, okay, with the exponential part. So let's come back. Now at rest, the momentum is 0. So here, the P is 0, so it simplifies, those equations simplifies that X is just this oscillatory components, so the X operator. You still have this alpha Dirac matrices, and V has this expression. So it is quite simple, but we will analyze it. It is quite technical because you have the notion of operator, Dirac matrices, etc. So it's not really straightforward to go to a visualization of what is going on behind it. So we'll go through it. To have a visualization, you need to take the eigenvalue of this operator to calculate the average value. This is really what Schrödinger did in his paper. When you have a quantum operator, when you apply the state vector, you get the eigenvalue. For example, for the energy, the Hamiltonian time psi is the energy psi. The same for the momentum for all spatial components. And when you take the expectation value of a quantum operator, it is given by this formula in quantum mechanics. So let's apply it for the velocity at rest. Here it is at rest. The velocity, as I mentioned, for each component, it is given by this formula. We take this expression squared. So you put away like this the term exponential minus I, etc. So you only get C Dirac matrices squared. The Dirac matrix squared is just the identity matrix, huh? So 4 by 4 identity matrix. So it's C is the speed of light, huh? I squared. And then you take the average value of this quantity. And when you take the average value, you just get C squared. Okay. And this is also what Schrödinger got. This means that you have a velocity operator means the average of this operator has eigenvalue plus or minus C. This really indicates that the internal motion of your electron on average, so the mean value is the speed of light. It's important to mention that is the average value because it's only by taking the average value that you get the speed of light. So meaning that maybe intrinsically in the electron you have some stochastic motion, I don't know, some random quantum fluctuation, and on average you get the classical values, so C. You can do the same
Olivier,
for the
Olivier,
yeah.
may I interrupt? So what's the physical interpretation of averaging? If I'm doing a single particle experiment, there is no averaging. So why is that formalism is considered to be like a single particle formalism when you do the average? Can you explain that a little bit?
Yeah, this is just at least this is have a look at the Schrödinger paper. It did this. In my intuition, it is that in quantum mechanics, it is what is behind the notion of operator. Maybe you have some quantum fluctuation that is behind the quantum operator. So you imagine some stochastic motion of the particle, and you only get physical observable and classical observable by taking this average of the particle. So even if it's for an individual particle, you can take the average of this quantity. The average is not for a high amount of particle, it's only for one particle. I don't know if it's clear or not. But this is still a subject that I'm not, it's not very clear for me. But yeah.
Right, and that's the explanation they give you when you learn these things. They tell you actually you do like like it's a multiple experiment, and then the average of that is actually what this equation is supposed to represent. But that's the ensemble representation. But now experimentally we can do we can track a single particle. So I'm curious whether this would apply to when you do like single particle experiments.
For me, yes, because this apply also for a single particle. For example, I will mention here after for the position operator, when you take the average, you get the amplitude for a single particle. This is also what Schrödinger mentioned in his paper. So, but we can discuss it later if you want. Maybe I'm not sure 100% sure of this, but yeah, this is an interesting question. Yeah, totally. This is also a debate of what is behind this expectation value in quantum mechanics. Yeah. So you see that when you apply the same for the position operator squared, when you take the average value, you get this value. This means that your eigenvalue is plus or minus h bar divided by 2mc. So it is a quantum wavelet divided by 4 pi. And when you have a look at the Schrödinger paper, you see that it mentions the same thing. When you put a bar here, it means that you take the expectation value. He calls zeta, it's the same notation as me, but he calls zeta for the amplitude. So the amplitude average is given by this formula, which is h bar divided by 2mc. Okay, so and this is the amplitude of what is called the Zitterbewegung motion. Okay. So if I go on, so this is what the Zitterbewegung equation told us about the electron at rest. Okay, so this means that you have a velocity which is the speed of light, an amplitude which is h bar divided by 2mc. Okay, so you have this factor 2 that sometimes it's quite forgotten by people studying this Zitterbewegung equation, but you have this factor 2 here that appear. Now, an interesting question is what do we get when you are in motion? So this means that if I come back to the Zitterbewegung equation, you have those two equations here. So this is the ones that apply in motion. Again, you have the longitudinal part, and you have this oscillatory part, okay? So let's study this. As before, we take the expectation value. For the moment, we just focus on the center of mass component. You take the expectation value, you use the normalization condition, and you get at the end c squared p divided by e, which is just the relativistic speed. Okay, so v. Okay, this means that it's interesting. This means that you have an operator at the quantum level, which is here it is the operator for the center of mass, and when you get the expectation value, you get the classical speed of the particle. So this answers your question, Yanis. This can apply totally to a single particle because you can define the classical particle of a single electron. So it's not the expectation value for a high number of particles. This means more, I think, that at quantum level you have some stochastic fluctuation, and on average, we take the average to get the classical value, I think. But I'm not 100% sure. But this is very interesting to study it, and for me, all the people that study Zitterbewegung should study this equation. And it's too much underestimated what Schrödinger did. So let's do the same for the Zitterbewegung component. We have this formula, we take put squared. I will not enter into detail, but you can see. And at the end, what is interesting is that you get this formula. So h bar divided by 2mc gamma gamma k. So this means that the eigenvalue of the Zitterbewegung component operator has eigenvalue h bar divided by 2mc gamma gamma k. Okay, and this is the formula. So if you don't trust me, I can show that Schrödinger obtained the same thing. It is this formula. You see that it took the amplitude squared, it takes the average value, and you get h bar divided by 2mc. With so this is gamma k and gamma. So why do we make the distinction between gamma and gamma k? Because gamma is just the Lorentz factor of the particle. Okay, so it is this means that for the particle you have a contraction whatever the direction of space, and gamma k, this means that you have only a contraction. This is also the Lorentz factor, but only it has only the non-null value in the direction of motion. So you have also a contraction in the direction of motion. This means that this formula means that you have a global contraction of the particle, whatever the direction of space. And in addition, in the longitudinal direction of motion, you have an additional contraction of the particle. Okay, so this is important. And I think this is what the main results that was obtained from Schrödinger. And Schrödinger also mentioned in his paper that apparently the amplitude of Zitterbewegung decreases as one approaches the speed of light. Okay, but here what is interesting is that you need to make a distinction between the different directions. Okay, so let's go on. Now, once we have those formula, we have those classical got those expectation value. Let's try to see how to visualize such motion. So let's take the case at rest. As we mentioned, at rest, the radius, the amplitude of this motion was h bar divided by 2mc. Here we use not classical, not complex expression, but with real expression, with cosine and sinus, with this parametric equation. Here you have the radius at rest. What is interesting is that the frequency, I didn't mention it previously, but here the frequency of the motion you can find it in this term, okay? Because the frequency is 2. It is mentioned here is 2e. E is the energy divided by h bar. You find it in the expression of the Zitterbewegung, okay? And so it is 2mc squared divided by h bar. So it is given, it is a very high frequency, Dirac and Schrödinger noticed it. It is given by this number, 10 power 21 hertz, okay? The velocity is the speed of light, we saw it in the formula. So this means that we would have a circular motion, okay, at the speed of light, okay, and the radius of this motion is h bar divided by 2mc, okay, and this generates a spin angular momentum that Dirac also mentioned, that it's a real angular momentum. And what is interesting is that when you take a motion at the speed of light at a scale which is just the quantum radius divided by 2, so this radius, you get a spin of h bar divided by 2. Okay, so this is for the case at rest. Now, what is it in motion? So maybe I will put it like that. So in motion here, we take just the case. Here you see that my circular motion is just in the xy plane, okay, xy axis, z equals 0. So now what I will do is that the particle moves in the z-axis, okay. So in the z-axis, so you would expect an helix motion, as was mentioned in the previous talk or also by Andras. You just get this equation from the Zitterbewegung equation. You have a contraction of the particle by this factor gamma. So this means that the radius here of the helix is slightly lower than the one at rest. And you have also a translation at the of the z component. So you have this motion. Here I just used just for the simulation a speed of alpha t. Alpha is just the fine structure constant. It's just an arbitrary velocity. It is the velocity of the electron in the hydrogen atom in the first orbit. Okay? So you see that here the transverse amplitude is given by this formula. This is obtained from the Zitterbewegung equation, and the frequency is given by this formula. So the frequency is higher in motion than at rest, okay, due to this gamma factor. Now let's do the same, but let's do a Lorentz boost not in the z direction, but for example in the x direction. It is a bit more tricky, but you get this formula. The z is still equal to 0, so z equals 0 here. The transverse radius, so y is just the same, so you have this contraction of this transverse radius, so h bar divided by 2 gamma mc in the sinus. And now this is the tricky part that was indicated from the Zitterbewegung equation, is that you have this translation of x, because you have here you do a Lorentz boost in the x direction, so you have vxt, but you have also this term with a gamma squared here, because here this is the amplitude in the direction of motion of the particle. This is the tricky thing that was indicated from the Zitterbewegung equation. And here I have put just the simulation, so you see that you have a circular motion, but you have also an additional translation in the x direction. Okay, so just don't hesitate to interrupt me if that's not clear, but the fact is that most of the people studying Zitterbewegung consider that you only have an helix possible. This means that the spin in this view is always collinear to the motion, but this is not the case. For the electron, the speed is not all the time collinear to the motion. It can take whatever direction possible. So in this particular case, it is collinear to the motion. In this case, the spin is perpendicular to the motion, but you can, those two cases are extreme, but of course you can have intermediate states with all the angles possible, angles between the plane of your helix and the direction of your motion. Okay. So again, this is not a model. It is just a direct interpretation of what is behind the equation of Zitterbewegung, and I truly invite you to really have a look, because you don't need to do a model, just create your own Zitterbewegung equation. It is already there, to be honest. So, and Schrödinger.
Schrödinger's model, Olivier. So let's try to keep it 7 minutes to 45, so that we don't.
So now let's go to let's try to study if those equations can give us information of what are the other information about the other particles, like the muon of the tau. just to be clear, the Zitterbewegung equation applies to all fermionic particle massive, elementary fermionic particle. So it applies also for the muon and the tau, of course, and because they are leptons, so they apply Dirac equation, and then they also satisfy the Zitterbewegung motion. So at rest, to remind you, the position operator and velocity operator are given by this formula. With the mean radius, again, when we talk about a radius, it is a mean, because it is taken by taking the average of this operator, so the average amplitude. You have this frequency that is given by this formula, and you have the velocities, which is the speed of light, as I mentioned previously. The difference between the electron, the muon, and the tau is just the mass. For example, the muon has a mass which is about 200 times the one of the electron. For the tau, it is this ratio here. So when you apply this scale of mass to the radius, you find that the radius of the electron is higher than the radius of the muon, and it's higher than the radius of the tau. And the frequency, you have the frequency of the electron is lower than the one of the muon. Okay. So this just indicates you what can be the difference in this approach between the electron, the muon, and the tau. The difference are the radius, which is related to the mass and to the frequency. Okay, so here, what is interesting is that the Zitterbewegung equation gives us information of the particle part of the, I would say, the Dirac particle. So it gives us information that you have motion at the speed of light. Okay, but you don't have any notion of here in this equation of a field. You don't have a field. You just have a trajectory. Okay, at the speed of light. Possibly in a circular helical motion, but in the Dirac equation, you have also this notion of field. So what is this field? This is what we will see here. You can have different approach of what can be this field. The first approach is just by considering the wave model that Debreu mentioned. He said that the particle can be assimilated to a small clock with an internal vibration in phase with its wave. So in this view, you would have just a wave, okay, that propagates at the speed of light, okay. When you confine a wave in a circle, it can form a standing wave. So I just here represented the standing wave, okay. Here it is given by this formula: 2 pi r equal n lambda, okay. So n is just the number of nodes. Here, just for simplification, I represented the 4 nodes, but just for visualization, okay. The wave has the following characteristic. It has a wavelength, it has a frequency. The energy of this wave is E equal mc squared is equal h nu. Okay, this is what Debreu said. It is this, that the energy is connected to the mass, but also to a frequency of the wave. Okay, so in this view, you can have a wave that propagates at the speed of light. It has a given wavelength. In this model, you can have that the wavelength of this wave is 4 pi r, because this is motivated to the fact that you have a spin 1/2 particle, so you have a spinor, so it is associated to a 4 pi symmetry. In the intuition, the wave needs two turns you need 2 turns to come back to the initial state, which is given by this formula. And when you apply it, you find that r equal lambda divided by 4 pi, and you get the right expression for the radius. Okay. So I don't say that is the truth, that I just say that it's quite relevant to have a wave model. You have a wave that propagates at the speed of light. So maybe it could be an electromagnetic wave, but the problem is that the electromagnetic wave doesn't have charge. So how does the charge is you introduce a charge? Maybe it could be what Adras said, a longitudinal and electromagnetic wave, maybe. So this is an interesting approach. And here it is the approach that we need a physical field psi. In standard quantum mechanics, psi is just connected to the probability to observe the particle. You know, the psi squared is just the probability. here in this approach, psi is really a physical field. Okay, let's take another approach. It is related to an approach from Dirac, Rousseau, and Bohm-Viguier. It's more related to hydrodynamics. First, it is we start from the analogies that was mentioned by Marc and Adras, from the analogy between hydrodynamics and the electromagnetism, that the ether can be considered as a superfluid without viscosity, that the vector potential is A, this is what Dirac say, is connected to the velocity of the fluid, so K is just a constant. The magnetic field is like a vorticity in the ether. Now, when you study the Schrödinger equation, it is interesting to mention that it can be reformulated in the Madelung equation in terms of hydrodynamical variable. Okay, so this is what Madelung said. I didn't put it in the equation, but Madelung equation, it's interesting. They are quantum Euler equation. So you take Navier-Stokes without viscosity, you have Euler equation, and Madelung equation are quantum Euler equation, which indicates maybe that Schrödinger equation is connected to the dynamics of something in a fluid. Okay, the wave function of a free particle in Schrödinger is given by this formula. So the amplitude E, this formula, and when you apply the position operator, the momentum operator is minus I h bar nabla, you get a velocity, mean stream velocity, which is given by this formula. V equals the gradient of the phase, P is the phase divided by M. Okay, this means that maybe there is some medium, a fluid that is flowing. The Schrödinger equation gives you the dynamics of this fluid, and when you take the average of the current, the stream velocity, the current, the velocity is given by this formula. So it is an irrotational flow because in this approach, you have no vorticity possible due to this formula in Schrödinger. Now, this is what Viguier, which is a French physicist, and Bohm said in his paper that I put the bibliography at the end. Now, when you take Schrödinger, but you use in additional some vortex, so you take an ether fluid, you add some vortex motion. They say in their article that such vortex motion provide natural model for equation with a spin, like a Pauli equation, okay? And when you take it relativistic generalization, you have the Dirac equation, okay? This means in this approach that when you take an ether fluid without any, which is with an irrotational flow, you have Schrödinger. But when you introduce some vortex motion, you get Pauli and the Dirac equation. And this is an interesting thing, is that when you consider a pressure wave in a rotating fluid, it is given by this formula. So the D'Alabertian, omega is the angular speed of the fluid, P is the pressure, and it is very analogous to the Klein-Gordon equation. Okay. So let's just say that in their model, it is a model of Viguier, Bohm, etc. They consider that they say that the particle could be a stable dynamic structure in this fluid. A stable vortex, the structure may be stabilized by some linearity. Okay, so you imagine that you have a vortex in the fluid. What is interesting is that a vortex is good to transport some mass energy in a high distance. Okay, but this vortex, here tourbillon is just a French, because the article is in French, unfortunately. But tourbillon means vortex, okay? Vitesse is the speed. So you take a vortex here in a fluid, but the vortex can propagate, it can over a certain distance, and the trajectory of this vortex could be a closed loop, okay? So you just take a vortex, you make it under a closed loop, and you get what is called a vortex ring or toroidal link. You can observe it. This is what Marc showed in this previous presentation with the dolphin. You have a vortex in the fluid. You can have it also in electromagnetism. You can produce some electromagnetic vortex ring. And in their model, you have this model here that it is the same. It's just a different representation. You have a vortex in the fluid. that forms a closed loop, where the radius of this loop would be the quantum radius. Okay, so this is quite connected to the Zitterbewegung motion, because here you have also a motion at the speed of light, but what you add is that you have a vortex in this ether, okay, that propagates at the speed of light, with the scale being the quantum radius, okay, and this would generate an angular momentum, okay, and maybe this vortex, of course, has some vorticity, and the characteristic size of this vortex can be related to what Marc calls the Fermi scale, so it is 10 minus 15 meters approximately. Okay. I think that's all for this. Here I have put some bibliography when you can find the articles that I mentioned, of the historical paper from Schrödinger of the Zitterbewegung equation, the article, the thesis of De Broglie, and the article of the analogy between electromagnetism and the fluid dynamics, etc. So let me know if you have some question. Thank you.
Okay, thank you very much. So we can have time for the one-shot question, and then John should start. Okay, so you can stop sharing, and maybe John can start sharing.
Yeah.
Okay. Okay, yes, you can. Yes, you can see.
I have to get set up here for a second. Oh, I'm trying to. Can you see my screen?
Yes.
Yes, okay. So I'm trying to get it to move. So, oh, here I go. Here we go. Okay. So first of all, I want to introduce myself. I'm not a physics professor like most of the other people. I was a former company president and somewhat of an inventor. I have 36 patents, built a company up to like 300 and some odd employees and so forth. And after I retired, I started to, my background is lasers and optics. So I got interested in physics in general, and I began to come up with a model of the universe. So I'm going to be touching on the Zitterbewegung, but it's in the bigger picture of the model of the universe. So my title here is Zitterbewegung creates an electron's gravity and electric fields. And so the technical paper that is the foundation of what I'm going to be talking about is titled Oscillating Spacetime, the Foundation of the Universe. It was released about 9 months ago, and it's received very good initial reception. In fact, it has received such a reception that now both Google and Bing have made a generic term where the term oscillating spacetime has become the term that they're now using for a single universal field. So if you're interested in reading the paper, you don't have to remember my name or the title. You just have to Google oscillating spacetime and you'll be taken to the discussion that is going on and so forth. So we're going to start off by talking about how many fields are required to build everything in the universe. Right now, the standard idea, the standard model is that, oh yeah, there's 17 overlapping fields. And this is a complex, somewhat messy idea. And I'm going to propose a new model of the universe, which has only one field. And this single field is a wave propagation medium. And in fact, it's a familiar field. It's oscillating, it's space-time, but it is the form of oscillating space-time that John Wheeler has proposed, where he says, okay, if you look at the vacuum zero-point energy oscillations at Planck frequency. And it's possible to take that simple phrase and turn it into a physics of what the oscillating space-time is made out of. So you're going to see this is term 10 to the 113th joules per cubic meter. So we have, in this case, what is called the cosmological constant problem, where quantum mechanics and quantum field theory is predicting this energy density, and yet the observable energy density is here. So this enormous dichotomy is considered the worst prediction in the history of physics. But I'm saying, oh no, it's really the best prediction. And the problem is that everybody is expecting, oh yes, if you have this much energy, you should be able to feel it, you should be able to touch it. And the answer is no, if it's a field, something is missing. And you have this as a medium that is the background for creating everything in the universe, but it is not energy itself. In fact, perhaps it's almost better to think of it as a pressure, because pressure and energy density have the same units. In other words, joules per cubic meter and newtons per square meter fundamentally are the same. And if you think of a pressure and has a tremendous pressure, well, then all of a sudden it has all sorts of things, but it doesn't require that you think of it as energy density. But in any case, what I'm saying is that the foundation of the universe is a sonic field that previously people were calling this ether, and the only function of the ether was to propagate waves, some light waves. But no, I have to make everything in the universe out of this one medium, so that I'm calling this oscillating space-time. So I then go in and I say, okay, if I need an acoustic medium, I need to know all the acoustic properties that it has. So first of all, if you have something that is Planck length oscillations at Planck frequency, well, multiply those two together, you get the speed of light. So physically, these little vibrations that are going on in space-time, they are happening at the speed of light, and therefore waves are going to propagate through this at the speed of light. But also, if you proceed with the calculations, you find out that you have a strain impedance, a displacement impedance, a bulk modulus, a virtual density, and a virtual energy density. I'm going to just mention that while I get this just from the form that, I'm saying that I'm starting with, it turns out that gravitational waves, if you look at the gravitational waves, they are encountering this same impedance. And this has been documented in several books on gravitational waves. So this is already a support that I'm onto something. Also down here, this virtual energy density, this really corresponds to the energy density of black holes, if I massage it a little bit. So this is another indication that we're on the right track. So I'm going to now be presenting a video, a little segment of a Richard Feynman lecture. And the reason I'm going to be presenting this, it's only 1 minute long. The reason I'm going to be presenting this is that it relates to what I am going to be talking about.
If we take the fundamental particles, such as an electron, any different ones will give different numbers, but to get an idea of the number, take electrons. 2 electrons, a fundamental particle. It's an object. It's not something I don't have to tell you what units I measure in. It's 2 particles that are fundamental particles. And they repel each other inversely as the square of the distance due to electricity. And they attract each other inversely as the square of the distance due to gravitation. Question: what is the ratio of the gravitational force to the electrical force? And that is illustrated on the next slide. The ratio of the gravitational attraction to the electrical repulsion is given by a number with 42 digits and goes off here. This is written very carefully out, so that's 42 digits. Now, therein lies a very deep mystery. Where could such a tremendous number come from? That means if you ever had a theory from which both of these things are to come, how could they come in such disproportion? From what equation has a solution which has, for one, 2 kinds of forces, an attraction and a repulsion, with that fantastic ratio? People have looked for such a large ratio in other places.
Okay, so Feynman says we have a very deep mystery. This ratio of forces, 42 digits. Who in the world could ever come up with such an enormous number? Well, actually, it turns out that my model is generating such a number, so that when I am dealing with waves and electrons and forces, I end up with this force ratio, and it turns out to be very simple. Here is the fine structure constant, and this is a term that relates to the strain amplitude of my electron model. It's a dimensionless number, and I'm going to show you how I arrive at this. I'm just giving you a little preview here, and here is the number that Richard Feynman was talking about. So I want to start off by going back to the very first reason why I started down this path. There was one day that I realized that if you had light in a box, and let's suppose you think of the reflecting box and you have a certain amount of energy and light in this, and you move this box, and you find out that it has many particle-like properties. For example, we've put the light in a box, so we've given it a specific frame of reference. A light wave that is freely propagating is going at the speed of light. It has no frame of reference. It has no mass and so forth. But when we give it a frame of reference, all of a sudden, that's a particle-like property. And it acquires not only that particle, but then it requires a rest mass or inertia. And by the way, you get this rest mass and inertia without needing a Higgs field. You also get all of the relativistic properties. You get relativistic length contraction, relativistic time dilation, relativistic increase in energy. And finally, you get de Broglie wave properties from, again, analyzing this light in a box. So it turns out that the first 5 of these really don't give us any hint of what the electron might be. You could put any wave in anything. But this last one, if you have to make a model of an electron and you demand that you have to get de Broglie wave properties out of your model, all of a sudden you've greatly shrunk the possibilities, and you then are forced to really start to look at a wave model. And I'm going to start off by changing from light in a box to light in a laser. So here we have 2 laser mirrors, and this is a frozen view for an instant, and this is a standing wave. We have waves going both directions, counterpropagating, but now we're going to start this. And it turns out that when it is moving, you no longer have the standing waves. You have, if you could see the waves inside there, you get a pattern like this. This particular pattern is what you would see if it was moving at like 5% the speed of light. The reason this pattern appears is that you have the Doppler shifted, so you've generated 2 different frequencies. So now I'm going to analyze this. I'm just going to take 2 propagating waves. They differ by 5% the frequency, and you end up with this beat that shows up. And this is all the characteristics of the de Broglie wave properties. So you can choose any frequency, but I'm saying you get a wavelength that is the beats here, and you also get 2 different speeds that it propagates at. So here we have a figure from this paper, and that is explaining that what I'm talking about is a modulation envelope, and that relates to the de Broglie properties. And also there is a speed that these waves are moving, and it's c squared over v. So these is an interference effect that's moving faster than the speed of light. This particular picture is for 5% the speed of light motion. So these waves would be going at 20 times the speed of light. You also get all the relativistic effects on these waves. Namely, here you have the length contraction. This is the famous gamma anyway. So now I'm going to go and say, do spherical standing waves create linear de Broglie waves? Before, I've just been dealing with lasers that are got 1 dimension. So I'm going to say here, I'm going to have waves expanding from here, and I'm going to now move this, visualize this moving. This particular simulation is about 25% the speed of light, and you see the Doppler effects that you get. So those are outgoing waves. I'm going to skip ahead to incoming waves. Well, you see now with incoming waves, the pattern has shifted. So now when we put both of these together, here's the outgoing waves, here's the incoming waves, and then the superposition of these 2 create this. These are exactly the de Broglie wave characteristics. They're nice linear waves generated from a spherical wave pattern here. So now the question is, okay, what do we need to actually match the electrons de Broglie waves? Well, we have to have the frequency of these waves correspond to the electron's Compton frequency. Then we get the wavelength right, and we get the speed right, and everything else. So this is what this says, that we get this if we have these matching. So now the next thing, we're going to skip ahead, and we're going to say, okay, now we're really getting into the inner workings of how can we get this electron model. I've skipped a couple steps, and I say, okay, I have two Archimedean spirals. One is a spiral that is waves going outward, and one is a spiral of waves coming inward. I need standing waves, and I have to have both directions. And these waves, these look like they're going to rotate opposite directions, but in fact, they're both going to rotate clockwise. It's just that when we have the incoming wave, so I'm going to turn this on and get, so we're going to bring these together. And magically, when we superimpose them on top of each other, it will then turn to the interference pattern that we get. So now this is what we get when we superimpose these two. You can see there is a central region, and it's surrounded by rotating waves here. This is a closer view of this. So in my electron model, this is the core of the electron down here. This is really the heart of it. It has like 99+% of the electron's energy. But this is making a disturbance in the surrounding oscillating space-time. So this disturbance is going to be the Zitterbewegung effects. And in fact, all of these waves out here are the result of the disturbance. We have waves going out, and this particular resonance condition has to have standing waves. So we have to have a reflection of these waves so that we also have the waves returning. And that's what then makes this pattern. So, however, as this model so far, it runs into one problem, which is that is what I'm calling a factor of two problem, which is that my model absolutely requires that I'm dealing with the Compton frequency. And yet, if we look at the Dirac equation, it predicts the center of mass of a wave packet representing electron exhibits a rapid oscillatory motion as Zitterbewegung at 2 omega, twice this Compton frequency. So here I'm going to analyze this as if it was a particle in a box. So we have these impenetrable boundaries, and I'm going to take this section where this is one complete wavelength. So this is the wave function if you had the particle in the box. But then when you go over and look at the intensity distribution, or you might say the probability of finding the particle, we're dealing with really twice the frequency. And not only is it, half the wavelength, but also the oscillations are in fact twice the frequency. So I'm claiming that the Zitterbewegung is in fact talking about physical motions. And in fact, if you, in an equation, I'm assuming that somehow you're going to find out that you need that factor of 2. So now I'm going to get back to the electron's core. In the paper, it explains that there is a Planck length distortion of space and also a Planck time distortion of space. Here is another way of simulating this. This is like, it is vastly distorted in the sense that these bumps should only be Planck length height, so that it's like 10 to the 20th times distortion here. But also it gives the wrong impression. It's not rotating in a single plane. It's rotating in a chaotic way so that it is really forming it has an expectation direction, but all the other directions, and it gives more of a spherical volume. So this wave is modulating both space and time. So now we're going to look and see, is there anything in nature that we can see that begins to look like the model that I'm getting at? Well, it turns out that if you have a superfluid and you introduce angular momentum into the superfluid, you get a rotating soliton wave. And here is a picture of a Bose-Einstein condensate. And these little tiny dots are little vortices. They're a couple angstroms in diameter. Each vortice has h bar angular momentum in it. And it turns out that this is quite a good model to start off for the electron, because it turns out, among other things, when these first are formed, when they first start to introduce these angular momentum, they use rotating laser beams. The these vortices are randomly distributed, but then over a couple seconds, they rearrange themselves into this, what's called a hexagonal lattice pattern. This hexagonal lattice pattern is making every vortex as far away from its neighbor as it can possibly be. In other words, each of these is repelling all its neighbors. And it turns out that the repulsion is really, I mean, now I've never heard anybody else talk about this, but I'm saying, hey, these forces are being transferred as waves through the Bose-Einstein condensate. There's no messenger particles, no virtual photons flying between these. Everything is being transmitted through the medium, and that's the way my particles are going to transmit forces also. So I'm going to jump ahead now and talk about how big is an electron. Well, electron has all sorts of mysterious sizes. If you collide an electron with a proton at an enormous energy of 200 gigaelectron volts, you discover that the electron appears to have a radius of something like 10 to the minus 18 meters. You can probe the internal workings of the electron by the internal workings of the proton by the electron. So in this case, the electron has to be smaller than the proton. Taking the other extreme, there's been double slit experiments where they have electrons going through two slits that are in the order of 10 to the minus 6 meters apart. And a single electron will make a diffraction pattern on the other side, a double slit diffraction pattern. So here you have a factor of 1 trillion between these two extremes. And we just say, oh, well, gee, this is just a mystery why the electron is this big. No. I have to come up with a model that explains how it gets this big, so that in my electron model, I have something I call a mathematical radius, which is when I'm doing calculations, I have to fix it into a specific radius. But then when it's in different boundary conditions, for example, if it's in a hydrogen atom, then in fact it adopts a different size, so it can change its size greatly. So now we have enough information to calculate the energy of this model. We know properties of the medium, we know the properties of the electron model. I take this wave equation, this energy. So this is a very simple algebraic equation that calculates the energy of a wave. And here we have the amplitude term, the frequency term, the impedance of the medium, the volume of the wave, and the speed of light in my case. And so now I take all the things I know. One of the ways of describing the electron amplitude is that it's Planck length. There's actually two ways. So I substitute Planck length in here and square it. I substitute the Compton frequency. I take the impedance. There's two impedances. I take the impedance that has to go with Planck length. I take the volume, and when I work all this out, lo and behold, I get this E equals h bar omega. I get the correct answer for the electron's energy. So that I think, I don't know if anybody else has ever taken their model and say, oh yes, now I'm going to see if my model, if I can calculate the energy, but I'm feeling quite happy. I thought I was finished with my calculations and everything when I got this. And all of a sudden I discovered that the model began to speak to me. It began to say, oh no, there's forces that should be generated. You should be able to calculate some forces. So then as I look at this model, I then say, okay, let's see if I have a central core here, and here is these, I can talk about the Zitterbewegung, and we have these waves, these standing waves going out, coming back. Now, if I say I put another electron out here someplace, there should be an interaction between this because we have this medium that they're both working in and so forth. So now I'm going to try and calculate what this interaction is going to be. The calculations are in the paper, but I can show you the answers, but to explain the answers, I have to be able to tell you two terms that I need. So that, first of all, one of the terms is what I'm calling the strain amplitude. Now, in a sine wave, you can express the amplitude of a sine wave two different ways. First of all, you can express the physical displacement that the amplitude is making. For example, the sound in air, you talk about what the particle motion is. In this case, the electron, it is displacing at plus and minus Planck length. But there's another way you can express the amplitude of a sine wave, which is you take the slope of the sine wave as it crosses the 0 point, and you take that, in this case, I'm going to use this as that slope, and it's Planck length divided by the the electron's Compton reduced wavelength. And this is the same as dividing it by the electron's Compton radius. So that this slope amplitude is this number here, 4 times 10 to the minus 23. So now we have enough terms so that we should be able to, or pardon me, I have to also define the distance term. And with humans, we define distance as meters. But I'm saying electrons define distance as the number of wavelengths. That's kind of their natural unit of measurement. So I'm going to define this script n as the number of reduced wavelengths between my central electron core and some other electron that is interacting in this. And this number then turns out to be this distance divided by the Compton angular wavelength, or the Compton radius. So for example, if this distance was 4 millimeters, then this number n would be roughly 10 to the 10th of these reduced Compton wavelengths between this. So now I'm going to then try to calculate the force between these two electrons, and I'm going to use this very simple force formula for waves: amplitude squared, frequency squared, impedance. Now we have the area of this second wave. So like I take the area of that smaller, I take the area over here, and then divided by the speed of light. When I do all this, I get this equation here. I was hoping that it was going to give me the force between two electrons with charge E. What in fact I got was the force between two Planck charges. Here, this is, by the way, this is Planck force. Here's the number of wavelengths. Here's this slope amplitude that I was talking about, and then that all gets squared. Now, at first, I was a little bit upset. Oh, yeah, I got Planck force. But no, then I said, no, actually, this is quite reasonable, because Planck charge is like the fundamental unit of charge. And Planck charge is the, if you interact with a photon, Planck charge has a coupling constant of 1. However, an electron has a coupling constant of alpha. So to change this into the Coulomb law for charge E, all I have to do is manually insert alpha here, which is 1 over 137. And then I have gotten from my model the force between two electrons. Now the big question is, does this model also generate gravity? Well, one thing about this oscillating space-time, it has got a boundary condition. It turns out that Planck frequency is the maximum frequency that this can have. In other words, if you physically say, what is with space, if we made light, we know the frequency of a laser. What is the shortest wavelength we can have? It's Planck length. The highest frequency is Planck frequency. It can't carry, we can't make anything more than that. Therefore, we have a boundary condition, and therefore we know that this oscillating space-time should be a nonlinear medium with this boundary. So we're now looking at some waves. I'm expressing here, this blue wave is a perfect sine wave. It's equal amplitude above and below the zero line. But now I have a distorted wave, a nonlinear wave. The equation for this is here. And so that the first term in this, in fact, comes down to here. This is the equation for the perfect sine wave. The second term is the nonlinear component, which is shown with this red here. You can see that it has always got a positive amplitude. There are additional terms in this nonlinear expansion, but right now I'm only going to use this one term. So what I'm saying is a wave in oscillating space-time should have a fundamental component and a nonlinear component. So here I go through, here is the fundamental component that, in fact, I've already shown you generates the electromagnetic properties, so that it is this strain amplitude sine omega t, the electromagnetic. And now I'm going to take this second term, the square term. This is going to be the gravitational component. So when I expand this, I have this amplitude squared. It's a number. It's not got any oscillation. This is, if I go back to, this is the displacement here. It's at half this distance. So that's the nonlinear portion. And then we have twice the frequency. So now I'm going to take, and when I plug everything into this equation here, except using my amplitude that I'm using from gravity, I then find out that I get this gravitational equation. And the only difference between this one and the Planck length, the Planck charge equation is the square term. So here you look, you see the same Planck force, the same number, the amplitude. But the big difference is that if you take this amplitude term, remember it was something times 10 to the minus 23. You square that, you get approximately 10 to the minus 45. You take this, you square this, you get 10 to the minus 45. You square it again, you get 10 to the minus 90th. So all of a sudden we're relating, we have a term in here that's going to make this roughly 10 to the 45th power smaller than this one. Well, then when we finally get down to the electron, we then have to plug in this alpha here, and the alpha then brings this thing back down to the point that we now can look at the Feynman's challenge. Here we have this, here is the equation for the electron, and it's got the alpha there. Here's the equation for the gravitational force between these, it's got the square. And now when we put these two, divide one into the other, we get this ratio. Hey, it is 4 times 10 to the 42nd power. We've succeeded. If Feynman was in the audience, I hope he would be clapping at this time. I don't know if to my knowledge, nobody has ever been able to achieve this success, but maybe they have. So what I'm finding is oscillating space-time makes many more predictions. All the gravitational wave equations correspond to the weak gravity approximation from general relativity. I said that I was only using the first term of this nonlinear expansion. If you want to add additional terms, I think you're going to get closer to general relativity. But using just the first term and talking about electrons, it turns out that this is accurate to 1 part in 10 to the 40th for electrons. So, hey, we don't need to get any better than that right now. So we have a few more predictions. It turns out that as I was looking at this, I was saying, oh, I should be able to calculate what I'm going to call a gravitational radius of an electron. And it is explained in the paper how I go about this, but I take this amplitude term, square it, and multiply it by this Compton radius, and I get a number, this number 10 to the minus 58 meters. It turns out this is, in fact, if you convert this here, this is really half of the electron's Schwarzschild radius. But in fact, it turns out that if you ever had a black hole that is maximally rotating, namely if you had a black hole made out of nothing but rotating photons, then the Schwarzschild radius of that would in fact not be 2 times the factor of 2 that they have in a Schwarzschild radius, but then you get down to just this number. So we have maximally rotating electron in here, and it's kind of reasonable that this would be its gravitational radius. There's all sorts of places that you can use this. I'm just using one example. If you take the equation for the effect on the rate of time, then you have this dt over d tau is 1 gravitational radius divided by the radial distance going out. So that this has been checked out as being a valid measurement of the electron's gravitational radius. There's another thing that I find as far as predictions that come that I find really absolutely proves that we have combined gravitational effects and electromagnetic effects. Suppose that we have 2 electrons that are some arbitrary distance apart, and we say, what is the gravitational force between these 2 electrons? Well, the gravitational force, we can calculate it, but for charged particles, this is the absolute smallest force that you can ever get from 2 charged particles for that separation distance we choose. So we're going to make a logarithmic scale of force, and we're going to take that infinitesimal force and put it at one end of this scale. Then we're going to go to the other end of the scale, and we're going to put Planck force, which is the largest force in the universe. If you have 2 black holes that are merging, at the instant they're merging and they're the same size, they in fact are experiencing Planck force at that final instant. So Planck force is roughly 10 to the 44th newtons. So it turns out that these 2 forces look nothing alike. So the question is, how does the electron's electrostatic force fit in here? Well, if you take the electrostatic force from 2 electrons, multiply it by the number of reduced wavelengths, and then multiply it by the inverse of the of alpha. So this is multiplying it by really 137. You end up precisely halfway, midway between these two extremes in forces. And I took an example of two electrons that were 6.8 times 10 to the minus 8 meters apart, so that I can then deal with Planck units. So this is a Planck unit of 1 in force. And at this distance, it turns out that this is 10 to the minus 100th of this, so that then we end up here. And exactly halfway between here, we end up with 10 to the minus 50 for this electromagnetic force. This is the equation here that's explaining all of that. So another thing that turns out, all of a sudden, that I'm on the roll of, oh yes, I think I've combined showing that how gravity is relating to electromagnetic forces, and once I get down to particles, it's obvious. And then it occurred to me that, well, wait a minute, suppose I had two Planck charges and some arbitrary separation distance. What's the force between the two Planck charges? Well, this is the force h bar c over r squared. Now suppose I have two Planck masses the same distance apart. What's the force that they experience? Well, it's exactly the same force. It's h bar c over r squared. Well, this is screaming, hey, no, when you get down to Planck limit, the gravitational force and the electrostatic force is the same. So that there, again, it's reinforcing the idea that we have merged these two forces. There's a final thing here that I just add on, and it turns out that if I take an electron and I say, I want to describe the slope of the gravitational curvature from distance r from the electron. So here we have distance r from the electron. So there's a slope, and this slope is in fact the weak gravitational approximation of the slope. But the slope is this amplitude term squared times the Compton radius. And in fact, this gives the weak approximation of this gravitational slope. So Einstein postulated, he says, oh yes, we're going to assume that matter curves a space-time round here. Nobody has ever figured out physically how we get this curved space-time. Hey guys, I think I figured it out. Here it is right here. This is the slope of the curvature. So anyway, the conclusion is oscillating space-time model proves that the electromagnetic and gravitational forces are closely related. I think this is somewhat historic. These new insights support the contention that the universe is derived from a single universal field. In other words, if you have only one field making everything, making all the forces, making all the particles, all of a sudden you should say, well, if we have one field, we should be able to understand how these are connected. In fact, as I was going through this, I had this vision of something like in The Wizard of Oz. They pull back the curtain on the wizard and you see the guy pulling the levers. Well, I felt like I'm pulling back the levers or pulling back the curtains when I'm peering behind the curtain of how the electron made the gravitational force and the electrostatic force. And in fact, this is what I've been telling you about. So this appears to be the start of a wave-based model of the universe, including quantum gravity without gravitons. So that's it. Thank you very much.
Okay, thank you very much. So there is now time for a very short question. And now Łukasz Bratek should start. So John, if you could stop sharing and
Yep.
Sure.
Hello, everybody.
Oh.
Do you hear me?
Yes, yes.
Yes.
I will open my transparency. I have to share it. I'm sorry, how to share this? I haven't used
green button.
Zoom before.
The green button at the bottom. There should be the big.
Oh yes.
Yes, yeah, we can see. Yeah. There was 1925 and now 2029.
Yes. Let me introduce myself. My name is Łukasz Bratek. I am based at Krakow University of Technology in Krakow, Poland, Faculty of Materials Engineering and Physics. And I would like to show you some model of ideal clock. It is a geometric model of particle with spin, which has its own Lagrangian, so its dynamics is completely defined. And from this, you can derive some idea of so-called chronometric curves. It is a helical curve in space-time, which shows the null vector connected with the spinor of electron, and the number of times it winds over the trajectory of the center of motion. Then you can, when it winds around it, you can calculate the number of times it runs the curve, and in this way you can define the phase of the clock and the time. I will show you this in more detail, but I need to introduce to you some representation of geometric quantities like vectors in space-time geometry as complex numbers. For example, when you consider a spinor with which we describe electron, then with this spinor is associated a direction of spinor, and this direction is described by a null vector. All null vectors satisfy this equation. These are equivalent on a point, on a sphere, on a unit sphere. So when you take at random a point on this sphere, you define a direction in space-time along which a photon propagates. So with all wave vectors of photons, you associate the null vector, the wave vector, and it is null. And it is represented by a point on this sphere, and this point shows the direction of propagation. Do you see the hand which I use as an indicator of these equations?
Yes.
Jarek, do you see?
Yes, we can see the pointer. Yes.
Yes, you see which equation I show. So here is a mapping from a point on a sphere to complex number. And with this complex number, I associate a null vector. So to every null vector, which is a point on the sphere, I associate a complex number. On the other hand, when electron propagates, it has some conserved quantities, namely the momentum and the spin vector. The two vectors have fixed lengths and which are determined by the mass and the spin of the electron, and are always the same independently of the state of the motion of the electron. So they are fixed once and for all. And with every such vector, like a spin vector, which is a space-like vector, you can associate a circle on the sphere. So every circle on the sphere represents a space-like direction. For example, a spin. So when we want to have a model of clock, we can use this picture. When we have a free electron, it propagates through the space-time. Its spin vector is conserved and is constant. And with this direction, we associate a circle. So we have a circle which is fixed in space. And when we take a point on this circle, we can, then this point represents a null vector, which is orthogonal to this spin vector. So we have a point which moves around this circle. This circle represents the spin, and the vector, the null vector, represents the direction of the spinner. So that when the spinner rotates, then a point moves on this circle, and this circle is fixed. And if the electron is in external motion, then the direction of spin can be changed. Also, the direction of the momentum can be changed. And with these two directions, which are connected with this electron, you can associate two null vectors. One null vector is a combination of the spin vector and of the momentum vector. And it is for this black point. And we can associate, consider also another combination of the momentum and the spin vector in the second point. And when we have free electron, these 2 points are then fixed. And then you can consider a Lorentz transformation, which leaves these 2 points fixed. And it is an elliptic transformation, which defines internal rotation of the phase of the spin of the electron. So in this way, I have a geometric model of phase of the Zitterbewegung motion of the electron. And now I define the phase of the clock. So the Z number is the null vector, the spinor vector, the direction which describes the direction of the spinor. And with the momentum vector P and the spin vector W, I construct two null vectors which are conserved during motion. And now I map these two null vectors to two complex numbers. These are chi plus minus. There's two complex numbers which are fixed. So let the spin vector be represented by this red circle. Then the spinor null vector is this green point which moves along this red circle. And this motion, this circular motion, is due to some Lorentz transformation. So when the spin rotates about the spin vector, we can define some phase. And this phase is defined here, the clock's phase. So we have the two fixed vectors, k plus and k minus, which represent the fixed momentum vector and the fixed spin vector. And we have also another kappa direction, which represents the spin vector, not the spin, yes, the spin vector, not the spin vector, but the spinor vector. So the k plus, k minus are defined by fixed momentum vector and fixed spin vector, and the k number represents the spinor direction. And this k tau 0 is some initial position of the spin vector, not the spin vector, but the spinor vector. And the k as a function of tau, the proper time, represents the spinor vector, the spinor position in another time. So in this way, because this ratio of 4 complex number is conserved by Lorentz transformations, so you can define in an invariant way the notion of a phase. So this is relativistically invariantly defined notion of phase of the clock, which describes the position of the spinor direction in the rest frame of the clock, but it is defined in invariant way, so you can measure it in every reference system. So we want to have some dynamics for this phase, and when we define the dynamics for this phase, then we have defined the dynamics of this clock. So this is the geometry behind this model of clock. The complex, the interpretation of on the complex plane. So we know how to calculate the phase. So how to calculate the phase connected with the internal circular motion of the electron. And if the time, the ideal clock hypothesis is fulfilled, then when the clock hypothesis is fulfilled, then this phase should increase proportionally to the proper time, independently of the state of the motion of this electron. But let's see if there is indeed some proportionality between proper time of the electron and the internal phase associated with the Zitterbewegung motion. We know from the Dirac principles of quantum mechanics some two important observations. The first one is that the expectation value from the internal velocity for the electron is always c, independently of the state of the motion. So the first postulate is that every particle, every relativistic quantum particle have to have this property, that with its motion will be associated some internal motion with the speed of light. So when you build some mechanical system, you have to assume this constraint, but as we will see, this constraint can be derived independently from some singularity between the Hamiltonian and Lagrangian pictures of the clock. So, and if Dirac says something like this, it must be very important, and it should be considered when you derive some model of a particle. So, when you define, if you want to describe define some geometric model of a classical model of quantum particle, you have to impose internal motion with the velocity of light. It is not possible for a particle which which is massive. So you have to introduce some additional degrees of freedom, and these degrees of freedom will be described by the direction of the spinor. So these are the internal degrees of freedom, and there are two such degrees of freedom. These are simply the two angles on a unit sphere. So these are internal spin degrees of freedom. And the other 3 degrees of freedom are associated with the motion of the center of mass. So the proper time is defined along the center of mass motion, and about this trajectory, we have associated another trajectory, a helical trajectory with the speed of light, which describes the states, which is associated with some internal degree of freedom, but with which we do not associate any mass. We associate this mass with the center of mass motion. So, having said this, I will show you the Lagrangian for a particle which has the when we look at this Lagrangian. It is written here, but I taken it from the Hamiltonian pictures of such geometric models. So, in order to define the simplest possible particle model, you have to define the position velocity. So this is the internal motion associated with the spin with the position on this light-like trajectory, the helical trajectory, and you have to impose this constraint. It means that the velocity vector is null. This constraint is independent of the reference frame, and it admits reparametrization of arbitrary parameter along this trajectory. Every relativistic system has to have this reparametrization invariance. So it is the first constraint. It is not imposed here. It looks like if I impose it here, but this condition comes from the inverse Legendre transformation. Is a singularity of the inverse Legendre transformation, which leads from the general Hamiltonian to the Lagrangian of any systems. And the Lagrangian looks like this, which you obtained. One describes the velocity. The other describes another constraint, which relates frequency of internal clock with the dynamical degrees of freedom. It is another constraint. When you do not impose the constraint, then you get different Lagrangians. And this Lagrangian, which I am talking about, looks like this. So, as Dirac says, when you have some constraints in your theory, the Lagrangian should include all these constraints. So we have independent, some internal variables. For example, this scalar product Kp. P is a momentum, but it is an arbitrary variable here because it is not yet determined by the dynamics. So when you change the P, this quantity changes. So it's some arbitrary quantity in your model, when you minimize this Lagrangian, then you obtain normal Lagrangian for massive particles with intermotion with the speed lower than the speed of light. So in the singular case, you have to, when you assume that these constraints are independent, then also this quantity is a dynamical quantity which is independent of the internal velocities. Normally, in a singular, non-singular case, this quantity Kp will be dependent on the velocities, and then you obtain some very complicated Lagrangian like this. This Lagrangian is a Lagrangian which classically describes a spinning particle model with fixed mass and fixed momentum, and its internal motion has velocity lower than the speed of light. And this Lagrangian is regular. In the singular case, you obtain this Lagrangian. And here is shown the motion in the Hamiltonian picture. The p vector is the momentum vector. The pi is a is a sort of spin vector which describes this the momentum associated with the spinning degrees of. So it's angular momentum, something like angular momentum, but in order to describe spin, we have to formulate so-called Pauli-Lubański spin vector, which is some combination of the momentum tensor and this pi tensor. But it is not now important. So n is some unit spatial direction, which also, like the k vector, is a way of representing the internal degrees of freedom instead of using k. Simply k is decomposed in p and in n. And when you look at the equation of motion, then you come to the conclusion that you obtain some internal motion on the sphere of null directions with some frequency determined by some fixed length. With this length, we can calculate the spin, or when we have the spin, we can calculate the length. So it will be, for example, in case of electron, it will be this length will be connected with the Compton wavelength of the electron. So with this is associated the internal frequency of this clock. So it is fixed by this number. This number is fixed, so this internal frequency is fixed. And when you have these constraints, and when you forget about this Lagrangian, you can construct some abstract notion, which I call chronometric curve. So these are space-time curves defined in the following way. When you have some motion in space-time, arbitrary motion in space-time, you can imagine that it represents some motion of the center of mass. So imagine that this red line represents the motion of the center of mass, whereas the blue line represents the internal motion with the speed of light. And this, when you have this curve given, this red curve given, and this can be arbitrary curve, then imposing these two conditions, like this and this, you can define a helical curve, which we interpret, and this the tangent vector to this helix is always null, so it represents the motion of massless particle. So with every curve you can imagine, this red curve, you can calculate, construct a helix about this curve, which represents the motion of the internal motion of the phase of the electron. So this is the geometric picture, and it is quite abstract. This is some kind of curve which you can analyze using the tools given by differential geometry. So this is quite mathematically well-defined theory of particular kind of curves, which we call chronometric curves. And these chronometric curves, we took this idea of these chronometric curves just from the constraints imposed by the ideal clocks, which are not arbitrary, but is a singular point of the general classical mechanics of geometric models of particles with spin. So this is very distinguished kind of motion of such particle. And you see also that you cannot define a simpler model. A simple model is only a point particle without a structure. The simplest possible structure which you can define in special relativity is given by a null vector. There is nothing which is more fundamental than a null vector in space-time geometry. And we know that with this null vector, we associate the direction of a spinor and additionally some phase, some internal phase. So we have 4 degrees of freedom, like 4 degrees of spinor. And there is no more fundamental thing like a light vector. So you cannot define simpler model which introduces spin on classical level. And now, how we define the phase? As I showed you before, this phase is defined here. K plus and K minus.
We're above 30 minutes. Maybe you take a couple minutes more.
I will finish in a few minutes. Look at this phase. This is defined by the spin vector, by the momentum vector. This is some initial position of the clock, and this is position of the clock at time tau, at proper time tau. Now, in order to define this phase, you have to define this angle at any position of the particle. But when you propagate a particle, its proper frame changes. So you have to propagate the information about the initial position of the clock using the so-called Fermi-Welker transport. So in order to define this phase at every instant of the motion, you have to compare this initial position of this clock but transported along this world line, along this red world line, via Fermi-Welke transport, and only then you can compare it with the actual number k. So you have to remember this. So, for example, let this represent the initial position of the clock, of the spinner. So you have to propagate this vector along this world line by applying Fermi-Welke transport and compare this with the actual phase of the clock. And in this difference gives you the clock associated with the Zitterbewegung motion. Now, the question is, I solved this equation of this propagation for the phase. For example, here I show you hyperbolic motion. So the center of mass is uniformly accelerated. Then you calculate the equation for the phase. I do not have time to say how to obtain it, but this is the equation. In this case, it's very simple. So this is the equation for the phase of the clock as the function of proper time of the center of mass. If there is no, alpha is the acceleration, but defined in the invariant way. So it's proper constant acceleration associated with this hyperbolic motion. So if this acceleration is zero, then the phase grows proportionally with the frequency, with the proper time. So the phase is proportional to the proper time, where the factor of proportionality is this frequency, internal frequency of Zitterbewegung. But when you have some acceleration, which this particle feels, then the solution is no longer linear. And this is the exact solution in this motion, which relates proper time of electron to its phase of its Zitterbewegung motion, so the internal clock. And you see that the proper time of the center of mass is not a linear function of the phase. Here it is expanded in a series with respect to the proper acceleration. You see the first linear grow with the proper time. It's the normal behavior which we expect when the clock hypothesis is not violated. And you have other terms which show you the violation as a serial expansion in the ratio of the acceleration, proper acceleration of this particle to some acceleration, c squared by the length, which is the acceleration felt by the associated with the Zitterbewegung motion. It is very extreme. I do not remember, but it is something like 10 to power 21 meter per square second. So it's enormous acceleration, which cannot be achieved in accelerations, in accelerator, maybe when, because alpha, the proper acceleration grows fastly as the speed of the proper motion of the center of mass is comparable with the speed of light. And you, on this plot, you have, on this x-axis, you have proper time, and on this y-axis, you have the internal phase. Normally, when the clock hypothesis is not broken, you have straight line. But you see, when the proper acceleration is great, then you have strong violation of this hypothesis. And if this hypothesis is violated or not depends in what direction with respect to the acceleration is directed the initial spin of this particle. I am now finishing. I have two more examples. This is circular motion.
10 minutes above, and you said 5 minutes ago you take.
I'm stopping now. This is the circular motion, and the same kind of motion, but on an orbit about a black hole. So you have evolution laws for the phase of this particle, and you can see that this clock hypothesis is again violated, with the exception of one case. Here you have definition of proper acceleration of a particle which moves around a black hole with proper frequency omega. Then when you have motion with Keplerian frequency, then the particle do not feel any acceleration because it is completely free in orbit, in free motion around a star. So in this case, this acceleration vanishes and the clock hypothesis is not broken. So, but summarizing this, you see that we can construct a toy model which originates from a dynamical system, which is associated, which is the simplest possible classical system, upon quantization, which leads to a Dirac equation. And you see that in this toy model, you can answer the question if this clock model can lead to something which violates clock hypothesis. It is a model with which you can test this hypothesis in different physical conditions. So that's all. Thank you very much for your patience.
Thank you very much. So please unmute and ask if you have any questions, comments, and then we can go to general discussion. Yes, sure. Adras, please just unmute and discuss.
Łukasz, is it possible to put in the chat the reference of the paper where you have? Is this published or is about to be published?
These results are not published yet, but the ideal clock model is given in the literature, and I give some reference in here. Here is the reference: relativistic ideal clock on archive. It is given on archive. You can see it, and there is defined the model of the clock. But the idea of the chronometric curves is not published. You are the first person which see this. But this was analyzed by my student who published this in his master's thesis. But I have to apply this to this model to some physical situations. I had no time yet for this. But you see that this model is mathematically well defined. This is the simplest possible model. You cannot construct something which is simpler in the classical mechanics of spinning particles with spin, and which has something to do with the Dirac electron, namely it has internal motion with the velocity of light, and it has all properties on classical level, which you would expect for a quantum particle like an electron. And there are two such Lagrangians, because there are two physical states, two helix you can wind around every space-time trajectory. So you have two kinds of such particles, like you have two kinds of electrons, the positron and electron. So you have to have, there are two Lagrangians for them. That's all.
So maybe I would have one question. What about the velocity of this point? Because
the center, I have the answer. The center of mass, it propagates with the speed lower than the speed of light. So the red curve here, it represents the motion of the center of mass, and it is always lower than the speed of light. But the motion, the internal motion of the Zitterbewegung, represented by this blue curve, is with the velocity of light, always.
Yes, but what about the radius of this structure? Because from the
this radius is given here. L is a Compton wavelength of the electron. The Compton wavelength of the electron.
Yes, the Compton. So
yes.
the
And with this Compton wavelength, you can associate the internal frequency of the clock of the electron. It is exactly the Zitterbewegung frequency.
The Zitterbewegung is here, and this is the model for the rest electron.
No, for any electron which can move about any trajectory you can imagine. You can consider here any trajectory, and you can define then the motion of the space, and you can count the number of times this curve winds around the center of mass motion. And in this way, you can relate the internal phase of the electron with the proper time of the electron, and they are proportional to each other when this red curve is curved. So if this center of mass feels some acceleration.
But isn't it the most fundamental model?
Yes, from the classical point of view, it is the most fundamental model you can imagine in classical mechanics.